In the shadowy void, Mars loomed quietly while 3i Atlas glided past, an outsider hailing from distant stars. The orbiting probe's lens activated, peering curiously at an odd sight. Absent was the usual dusty haze or radiant halo around a comet. Instead, just a subtle, spectral blur, so bizarre it rattled even veteran skywatchers. Officials reacted quickly. ESA's prized venture, the JUICE probe, received instructions to veer off course and observe. What enigma demanded this haste? What lies behind that streak in the emptiness? This evening, we chase the enigmas concealed in this initial snapshot. Stick around, and I'll reveal why it shouldn't have appeared like this, and why that's more significant than most realize. Section 1. Captivating Intro and Recent Events. On March 27, 2025, the European Space Agency unveiled a photo that defied expectations. Not due to equipment glitches or missed opportunities, but because the details in those pixels clashed with virtually all predictions astronomers held for a comet traversing the solar system's inner reaches. Captured by ExoMars Trace Gas Orbiter, a vessel built to detect methane on the red planet, not snap pics of cosmic intruders, there emerged a hazy speck amid the blackness. It required merging scores of extended shots, as the subject shone 100,000 times dimmer than Mars terrain beneath it. What grabbed attention right away wasn't the visible elements, but their absence. No trailing streamer, no vast expulsion of particles and vapors extending millions of kilometers from the core. No luminous curve marking the comet's journey across the cosmos. Merely a tight cluster of glow, hazy and strangely balanced, lingering in the view as if oblivious to standard comet protocols. To understand, recall how classic comets behave near the sun. Stellar rays warm their frozen exteriors, vaporizing trapped ices into the vacuum and towing along fine debris. Then, the sun's particle stream sweeps this ejecta from the heart, forming those stunning appendages we link to comet arrivals, the sorts that ancient cultures saw as portents, adorning star charts and sparking awe. 3i Atlas was meant to follow suit. As the third verified interstellar wanderer from outside our solar system, spotted approaching in July 2025 via the Atlas Detection Array, its path proved it came from afar. Ejected eons ago from some alien star's domain, it's now slicing through our stellar backyard at 86 kilometers per second. Upon hitting Mars' range, about 228 million kilometers from the Sun, a proper comet ought to display clear signs of activity, with the tail fluttering like a flag to signal its arrival. Yet 3i Atlas pulled up muted and streamless, based on ExoMars views. The core stayed indistinct, so the craft couldn't separate the rocky form from the encircling coma, that gaseous, dusty sheath that usually cloaks lively comets. ESA's tools only verified a presence, a dim radiance, emitting a coma, yet skipping the tail extension. Experts anticipated a show, they encountered a puzzle. Harvard's Avi Loeb had foreseen such a twist. Through Medium articles dropped weeks prior to the ExoMars glimpse, Loeb highlighted quirks in 3i Atlas's actions, like erratic luminosity shifts, potential forward sprays misaligned with solar warming, and orbit traits that strayed from typical comet frameworks. Loeb's track record speaks volumes. He once argued that Oumuamua, the inaugural spotted interstellar guest in 2017, could be engineered, maybe a solar sail or scout from alien tech. Most scientists pushed back, opting for earthly ideas such as nitrogen chunks or hydrogen vents. Still, Loeb's openness to wild theories positioned him as the key figure for pondering if this is more than a mere rock. Thus, when 3i Atlas materialized far from forecasts, his prior alerts resonated louder. The core puzzle boiled down to one stubborn query. Why does this thing evade comet appearance, despite its path and makeup screaming otherwise? Just a viewing quirk? Maybe the tail aligns straight toward or from us, hiding out of sight. Or could this signal true oddity, an entity resisting labels because it shuns our tidy natural categories? ESA stoked the buzz with a surprise move. They disclosed redirecting JUICE, the Jupiter Icy Moons Explorer, a €1 billion powerhouse en route to the gas giant, for a detour to scrutinize 3i Atlas. Consider the implications. JUICE isn't geared for comet studies. its instruments designed to probe the frozen exteriors of icy moons and the swirling fields of Jupiter's magnetic domain. Altering the course of such an expedition, even for a short while, demands extensive coordination, thorough evaluation of dangers, and solid rationale. That the European Space Agency viewed this as valuable enough to pursue indicates they spotted an anomaly compelling enough to stray from the planned itinerary. The press release tied to the redirection employed deliberately even-handed wording, mentioning the sighting caught all parties off guard, a subtle official nod to how 3i/Atlas had thrown experts into disarray. This haste points to underlying intrigue. Initial readings might have uncovered traits calling for prompt investigation. The missing trail could have sparked worries that this entity isn't quite what it seems. Or maybe researchers just seized a unique chance to examine an outsider from another star system using several probes at once. The theories practically compose themselves. If an intelligent society aimed to dispatch a scout to scrutinize distant stellar realms, what form might it take? You could encase it in frost and grit, masking it as an ordinary hunk of space junk. Limit shiny bits to dodge early spotting until the last moment. Craft it to emit vapors deliberately, forming a hazy envelope for added cover without the obvious streak that screams artificial. Pure conjecture, naturally, fun to ponder but lacking evidence. Still, the puzzle endures since the findings resist easy, everyday interpretations. The oddities go beyond visual quirks. They spill over into spectral analysis, light polarization, and motion patterns. Each data point piles on more enigmas instead of clearing them up. And that's precisely where this narrative kicks off, at the crossroads of what we detected and what we anticipated detecting. Amid the comforting reliability of orbital physics and the jarring truth that the cosmos occasionally tosses us items that ignore the manuals. When observations clash with models. When a cosmic drifter won't play by the rules. Those inquiries will propel the rest of our exploration as we plunge into the readings, the debates, and the slim yet intriguing prospect that 3i/Atlas signals more than our grasp of icy wanderers, rubble, and the cosmic flotsam wandering the voids between suns. Part 2. A quick overview of the observation schedule so far. The tale of 3i/Atlas doesn't start with ESA's baffling snapshot, but stretches back several months to the routine patrols of automated scopes scouring our planet's night sky for hazards and oddities. On July 1, 2025, the Atlas, Asteroid Terrestrial Impact Last Alert System, survey picked up a shifting blip that failed to align with cataloged rocks or icy bodies. In mere hours, rough path estimates unveiled the remarkable. This wasn't a homegrown solar system traveler. Its speed, direction, and arc pointed to origins from outside, marking it as merely the third verified outsider to zip through our stellar neighborhood in human annals. The find ignited buzz throughout astronomy circles. Such extrasolar intruders are incredibly scarce, or more accurately, nailing them down is a tough feat. They zip along speedily, stay dim, and offer narrow viewing slots before vanishing into the interstellar black. Oumuamua in 2017 blindsided the field, slipping away sans in-depth scrutiny. 2i/Borisov in 2019 yielded richer info, but stirred fresh puzzles on comet variety. Now, 3i/Atlas supplied a third benchmark, an opening to sharpen our picture of what other worlds hurl out and how those castaways act on their fleeting jaunt past ours. Hubble Space Telescope sessions kicked off right after verifying its alien path. The veteran scope, after years aloft, still delivers stunning light measurements and chemical breakdowns. First glimpses captured a subdued form wreathed in a subtle haze, positive indicators that 3i/Atlas was stirring, vaporizing ices as it neared the sun's warmer zones. Yet a peculiarity emerged in the hue metrics. Those brightness contrasts across various filters that disclose makeup and shine. The tones veered a touch more crimson than usual, suggesting grit traits or mixes diverging from our local comets. Next, the James Webb Space Telescope directed its heat-sensing eyes at the intruder. JWST, our latest and mightiest eye in the sky, shines in spectral dissection, splitting rays into hues to pinpoint molecular fingerprints. The opening profiles disclosed a shocker. CO2 overwhelmed the haze vapors at 8 times the level of H2O steam. This flipped balance stands out. Typical comets in our surveys feature water as the top sublimating agent alongside carbon dioxide. Oxides took a back seat in the composition. Comets typically get labeled as grimy snowballs, highlighting the water ice that makes up most of their mass. Yet with 3I/Atlas, it appeared to be releasing carbon dioxide ahead of everything else, pointing to either an odd makeup or peculiar vaporization patterns influenced by its origins beyond our solar system. As the season shifted from summer to the start of fall, 3I/Atlas kept heading closer to the Sun, crossing Mars's path in the beginning of October 2025. This nearness opened up a rare chance. Mars has several satellites circling it. NASA's Mars Reconnaissance Orbiter and MAVEN, ESA's ExoMars Trace Gas Orbiter, and Mars Express, all fitted with imaging gear and analyzers. Though these probes weren't built for studying comets, the teams in charge spotted the potential to snap pictures of an outsider from an exceptional angle. They set up viewing slots, arranged scope access, and figured out the adjustments for direction. The ExoMars Trace Gas Orbiter got tapped for detailed shots via its CASIS imaging setup. The hurdle was clear right away. CASIS had been crafted to snap pics of Mars's terrain: ridges, impact sites, channels, spots that bounce back plenty of light for sharp details. In contrast, 3I/Atlas was roughly 100,000 times dimmer than usual subjects. Getting any worthwhile shots meant maxing out the tool, layering several extended captures to gather sufficient light over the background clutter. It echoed the methods hobbyists use for snapping faint celestial bodies, but here it was a probe around a distant world, following a shifting target across vast distances in kilometers. As the probes maneuvered into place, Earthbound scopes kept up steady watch. Tracking shifts in brightness over periods uncovered a 16-hour cycle, indicating the core spins once every 16 hours, flipping end over end with subtle glow fluctuations that suggest an irregular form. Such data poured in from scopes worldwide, linked via casual collaborations where stargazers exchanged info almost instantly, aware that brief cosmic guests call for teamwork. All along this stretch, Avi kept offering updates via online writings and talks. He pointed out the absence of a clear tail, even as 3I/Atlas neared ranges where vapor release ought to ramp up. He puzzled over the glow patterns, proposing the thing could be bigger or shinier than what usual models forecast. He linked it to Oumuamua's quirks, arguing that spacefarers from afar keep bucking our assumptions, maybe due to unique birthplaces. Or, though he didn't spell it out, he hinted that not every one is purely natural. The general audience tuned in keenly, fueled by past buzz. Oumuamua had gripped minds just for being so bizarre. Its stretched outline, erratic spin, odd speed-up leaving the sun's sands clear gas bursts. Discussions on its origins flowed from research papers to news outlets, with titles probing if we'd spotted our initial visitor from another star system. 2I/Borisov eased things by acting normally, yet it left folks let down too. Where were the wild reactions, the offbeat traits, the sign of a genuinely otherworldly arrival? 3I/Atlas looked set to blend the two, lively enough to qualify as a comet, peculiar enough to keep theories alive. By the end of March 2025, excitement mounted for the ExoMars image drop. Early updates indicated the effort had paid off, overcoming gear hurdles as CASIS had snagged an image through the dim haze. When ESA shared the visuals at last, skywatchers huddled at displays, anticipating a classic comet scene. Outgassing, spewing material, dragging its charged trail through the sun's breeze. But what emerged was that tight, tail-free smudge, blurry and puzzling, balking at the expected show. This sequence highlights a key aspect of today's stargazing field. We're in a time when spotting something new moves fast, yet grasping it unfolds gradually. Mere hours after the find, we confirmed 3I/Atlas came from interstellar space. Days later, readings exposed quirky elements. Weeks on, glow profiles outlined its spin. Still, after months, core puzzles linger. Is it truly a comet, or otherwise? Why the off-kilter appearance? What story does its makeup reveal about where it came from? These linger since raw info falls short of insight. Making sense demands frameworks, side-by-sides, arguments, and typically years of scrutiny before agreement forms. And with ESA's shot displaying an item that resists simple labels, the saga shifts gears. The enigma grows instead of clearing up. Oddities pile on rather than explain away. And the chance that 3i/Atlas stands for something truly out of the ordinary, be it a natural oddity or a more intriguing anomaly, has transitioned from marginal conjecture to a serious topic in scientific inquiry. The subsequent developments in this sequence will hinge on upcoming observations, ongoing data reviews, and ongoing discussions in meeting halls and online forums throughout the astronomy community. Section 3. The ESA's ExoMars image. Its revelations and omissions. The ExoMars Trace Gas Orbiter's capture of 2I/Borisov involves layering several multi-second shots to amplify the signal beyond the detector's noise floor. From this composite arises a dim glow, less sharp than a star, somewhat blurred, clearly spread out, shifting relative to the stellar backdrop during the imaging run. The core body stays indistinct, as the instrument failed to distinguish the solid nucleus from its enveloping haze. All that's visible is this sheath of vapor and debris, a nebulous shroud stretching maybe hundreds to thousands of kilometers from the central mass. The most notable omission is the tail. As comets near the sun, they form two kinds of tails. Solar radiation pressure ejects dust grains from the nucleus, forming a bent curve that follows the orbit's trajectory for the dust tail. The ion tail emerges when the solar wind, a flow of ionized particles radiating from the sun, yanks charged atoms from the haze and pulls them directly anti-sunward, yielding an azure streak that might stretch millions of kilometers. For an active comet at Mars range, both should show up, given typical dust output and gas release. 2I/Borisov displayed none. Its haze seemed balanced, contained, without stretching or flow in any direction. No vague streak in the sun-opposite way. No gentle curve following the path. Merely a hazy patch that might mimic a distant galaxy or cloud if its identity were unknown. ESA experts scrutinized the images, deploying diverse enhancement methods to tease out subtle patterns. Yet the tail stayed hidden. If present, it was either too weak to detect or aligned exactly toward or from the probe, compressed out of sight by perspective. Tails are crucial for diagnosis. Dust volume in them gauges release rates, the mass ejected per unit time. Their form clues in on grain dimensions and speeds. Spectroscopic analysis of tail composition pinpoints subliming compounds and their ratios. Lacking a detectable tail, scientists must deduce activity from the haze only, which proves challenging since it can be opaque, obscuring the core, blending various light sources, and shifting with angle. Instrument constraints further muddle things. ExoMars Cassis is tuned for Mars terrain wavelengths, not dim comet glows. Though superb for its main task, the sensor's contrast and responsiveness falter on targets 10,000 to 100,000 times dimmer than usual. Noise dominates here, erratic pixel variations that feign or veil subtle details. Combining shots cuts noise but can't erase it fully. Part of the absent tail could just lurk beneath the sensitivity cutoff, unseen not due to absence, but from insufficient signal strength against the static. Still, the haze's even shape raises concerns. Even sans visible tail, one anticipates some stretching, some directional cue in the outer edges, where material shifts from tethered to free, where sunlight starts repelling bits. The haze appears nearly round, implying either minimal output, so scant that particles linger close instead of drifting off, or an angle that masks all unevenness. These ideas work, yet demand precise setups that seem contrived. The haze's density heightens the mystery. Standard comet envelopes sprawl well past the nucleus, frequently spanning tens of thousands of kilometers with fading intensity outward. 2I/Borisov seems more confined, focused, as though the vapors and grains disperse less readily than anticipated. This might point to atypical expansion speeds. CO2 evaporation could yield gentler spread than H2O, or it may hint at odd grain traits, like clumping or electric charging, reshaping their behavior. The images release sparked swift, expected buzz online. Platforms buzzed with parallels to Oumuamua, another tailless wanderer that fueled talks of non-natural sources. The term alien hints of enthusiasm popped up in online discussions, even as the European Space Agency steered clear of such wording in its formal announcements. Experts highlighted the hurdles in detection and the constraints of remote viewing, calling for restraint and careful analysis. Still, the oddity of that image was impossible to ignore. It didn't resemble a typical comet, not based on the long-established theories and data from our solar system's icy wanderers. Yet astronomers occasionally whisper about an alternative idea, hesitant to promote it without solid proof. Suppose 3I/Atlas isn't mainly a comet after all. Imagine it as a sturdy, rocky core, maybe laced with some frost that releases gases faintly, forming a fuzzy envelope without the intense vaporization required for a visible tail. That would align it more with asteroids than comets, though boundaries fade for far-flung travelers that don't slot neatly into familiar categories. Oumuamua sparked comparable arguments, deemed a comet by certain researchers, an asteroid by others, and a total unknown to plenty more. The impending JUICE flyby holds real importance because it provides a fresh perspective, new tools, and a chance to spot any delayed or sporadic tail activity. JUICE will scrutinize 3I/Atlas from varying distances to the Sun, diverse viewpoints, and multiple spectral bands. Should a tail emerge, the puzzle leans toward everyday causes. Perhaps alignment or schedule hit it from ExoMars' gaze. If no tail shows up, the intrigue intensifies, pushing scientists to devise bolder theories for an object that's evidently venting yet skips the classic sign of cometary behavior. Inevitably, thoughts wander to bolder notions. If 3I/Atlas were engineered, say, a spacecraft, light sail, or relic tech, what might it resemble? Unlikely a polished vessel from sci-fi tales. Instead, it could be dusted over from eons in the void, maybe deliberately camouflaged to mimic natural debris, or simply eroded by tiny space rocks and radiation. It could release vapors from embedded ices, generating a haze that conceals its origins. A tail might be absent if the emissions stem from onboard mechanisms rather than sunlight, dispersing fumes and patterns that ignore the usual away-from-sun alignment. This remains pure conjecture, fun to ponder, but lacking backing. Mainstream science holds firm that ordinary origins are far more probable. Comets abound. Ejections from other stars happen often. Odd makeups make sense amid the galaxy's varied worlds. Claiming artificial roots demands ironclad proof. Not mere quirks, but ones that resist every natural account, plus clear markers of design, like symmetrical shapes, deliberate broadcasts, or exotic substances. Still, that stubborn image defies predictions, appending our cozy ideas about alien intruders. And maybe that's the true takeaway from ExoMars. Our frameworks rest on scant evidence. Each arriving outsider will surprise us. The cosmos teems with wild variety beyond our local bubble's tame familiarity. The tale could materialize soon, settling things into routine science. Or it might stay hidden, fueling endless questions about a quirky visitor that sustains our curiosity, bridging the divide between sighting and insight. Part 4. Retasking JUICE and its significance. The Jupiter Icy Moons Explorer had no comet watching on its agenda. Launched in April 2023, JUICE focused solely on probing Jupiter's frozen satellites, Ganymede, Callisto, Europa, hunting hidden water worlds, dissecting icy terrains, charting magnetic influences. Packed with 11 specialized tools tuned for gas giant studies at Jupiter's range, not comet chases in the inner system. Its path involves intricate slingshots from planets en route to Jupiter in 2031. Every adjustment planned long ahead, every viewing slot reserved, every fuel drop tallied for core goals. Thus, ESA's move to pivot JUICE toward 3I/Atlas raised plenty of eyebrows in the planetary research world. Far from simple, this shift meant thorough hazard evaluations, tech audits, sensor tweaks, and above all, a strong rationale. Why divert effort to something beyond the main brief? What payoff warrants the added hassle? ESA's choice to go ahead underscores a key point. They saw 3I/Atlas as a rare chance worth the effort, risks, and demands, no matter what. The schedule aligned perfectly in JUICE's favor. The probe is presently navigating the inner solar system amid its initial Earth gravity assist maneuver, coming fairly near the path of Comet 3I/Atlas. This flyby demands no significant engine burns, only minor orientation tweaks to aim the onboard sensors toward the object. Though the separation spans millions of kilometers, the craft's imaging systems and analyzers are optimized for vast cosmic distances, capturing features that elude Earth-based scopes. The viewing period spans multiple days, offering repeated opportunities and varied perspectives as the spacecraft and comet follow their orbital paths. What sets JUICE apart from typical observatories? For starters, it enables multi-band photography, snapping the comet's fuzzy envelope and possible extension in both visible light and near-infrared at once, which uncovers hue variations hinting at dust makeup and grain dimensions. Additionally, spectral analysis via tools like MAGIS and UVS delves deeper into the envelope's molecular makeup than prior efforts. Sequential light measurements monitor fluctuations in luminosity, potentially linked to spinning or sporadic gas releases. Polarization scans gauge light diffusion from particles, yielding insights into their shape and makeup. The gesture carries weight beyond science. Deploying a €1 billion endeavor from ESA isn't a casual choice. Opting to redirect JUICE signals an agency consensus that 3I/Atlas merits rigorous study. It signals trust in the comet's value, alerting the global research network that this goes beyond fleeting interest or press buzz. It's a priority for elite missions. ESA's press release, noting the surprise for all involved, implied a deeper message. This caught us off guard. We're treating it with gravity. We're committing premier resources because it matters. Historic comet probes offer benchmarks for JUICE's potential contributions, despite the remoteness. Rosetta circled Comet 67P/Churyumov-Gerasimenko for 2 years, unveiling nuances in cometary structure, ice dynamics, vapor emissions, and development. Deep Impact slammed an impactor into Temple 1, bearing hidden frosts and probing the resulting debris cloud. Stardust gathered particles from 81P/Wild and brought them home for lab scrutiny. Such ventures reshaped comets in our minds from distant specks to intricate, evolving entities. JUICE can't match that intimacy with 3I/Atlas. The gaps are too wide, the observation slots too brief, but even basic profiles would push boundaries forward. The intriguing queries JUICE could tackle abound. Might the extension appear from a new viewpoint, solving the puzzle through mere perspective? Could the envelope's makeup evolve nearing perihelion, showing how ancient interstellar ices react to solar warmth? Any unforeseen outflows? Maybe compounds unseen in local comets. Traces of odd reactions from the dense disk origins of 3I/Atlas? Could polarized views validate or challenge the peculiar particle traits noted before? Detection of lagging or burst-like behavior is also feasible. Comets aren't predictably steady. They can surge with rapid vaporization, possibly from buried gas pressures, icy ledge failures, or spins exposing untouched surfaces to the sun. If 3I/Atlas teeters on the edge of detectability, just enough fuzz but no defined stream, a sharp activity spike might yield striking shifts visible to JUICE. The extension could ignite abruptly, shifting the body from oddity to standard comet in mere hours. Pondering ESA's behind-the-scenes drivers sheds light. They weren't obligated to publicize the JUICE diversion. Plenty of satellite views occur discreetly, surfacing in records long after without notice. By spotlighting this, ESA likely sought to rally awareness, maybe cueing other setups for joint efforts, or to temper views on the main mission schedule, or to highlight agility toward fresh prospects. The announcement alone underscores their regard for 3I/Atlas as noteworthy enough for openness. A subtle rivalry lurks too, even if experts downplay it openly. Various groups and instruments are eyeing 3I/Atlas, Hubble, JWST, telescopes across the globe, Mars satellites. ESA's inclusion of JUICE guarantees Europe's stake in premier-tier data, claiming shares in analyses and publications, while bolstering its role in interstellar studies. Agencies team up, yet they track prominence keenly. Scientific recognition and acknowledgement will flow from the JUICE mission's findings. Observations gathered by JUICE are set to yield publications featuring author teams from the European Southern Observatory, along with conference talks and media announcements highlighting Europe's role in the discovery. The response from the public to the mission's redirection has been positive and supportive. Folks grasped the significance right away. When a €1 billion probe aimed at Jupiter gets repurposed, it signals that something truly noteworthy is unfolding. The storyline evolved from researchers showing casual interest to experts rushing to gather data. This air of haste, whether genuine or just apparent, amplifies the notion that 3I/Atlas stands out as exceptional. It underscores that the peculiarities spotted in early readings demand swift investigation. It also implies that the chance to gain insights could vanish if we fail to deploy assets promptly. Ultimately, the revelations from JUICE are unpredictable, hinging on factors like the alignment for imaging, the functionality of onboard tools, and how the object itself acts. In the best-case outlook, JUICE would snag sharp photos revealing a developing tail, spectral analysis verifying standard cometary makeup altered by its interstellar origins. Polarimetry could clarify the characteristics of the dust via ordinary processes. Such results would dispel the enigmas around 3I/Atlas, classifying it solidly as a fascinating yet natural phenomenon and shutting down wilder theories. On the flip side, or maybe it's the more thrilling option if you thrive on unknowns, JUICE might validate the irregularities, depicting a comet without any persistent tail, sporting bizarre chemical signatures and dust traits that resist straightforward interpretations, thus intensifying the mystery instead of solving it. Regardless, ESA's choice to prioritize this flyby carries weight. The organization doesn't squander prime assets on every celestial oddity that pops up. Funding is tight. Slots for observations are highly contested. Proposals require ironclad reasoning. The fact that JUICE was reassigned indicates that experts at ESA reviewed initial datasets, identified elements demanding deeper study, and persuaded leaders that the potential knowledge outweighed the logistical hurdles. Time will tell if that judgment was spot on or a bit premature, as the incoming JUICE information gets processed and specialists dive into the meticulous task of teasing genuine patterns from background clutter, reality from illusions, and comprehension from raw sightings. Part 5. Avi Loeb's focus on anomalies and their tie to this latest sighting. Avi Loeb has always been forthright in posing tough inquiries. The Harvard astrophysicist earned his initial acclaim through conventional work on black holes, the cosmos's infancy, primordial stars, before shifting to technosignatures and the hunt for alien life. His 2018 study suggesting Oumuamua could be engineered rather than a natural body thrust him into the spotlight and debate, praised by fans of daring ideas, dismissed by advocates of restraint. With 3I/Atlas's arrival, Loeb was geared up to probe it for irregularities, issuing a string of medium articles that detailed quirks evident in basic preliminary scans. The initial oddity Loeb pointed out was the total absence of a tail, even in initial Earthbound views. Typically, comets display at least a subtle tail by the point they reach Mars's path, provided they're undergoing active ice vaporization. Yet, 3I/Atlas revealed zilch. A few watchers mentioned potential slight stretching in select frames, but it was inconclusive, easily chalked up to interference or image handling glitches. Loeb observed how this tailless trait echoed Oumuamua's pattern, the prior interstellar guest that showed no detectable tail even after a close solar pass, where any frozen material ought to have boiled off energetically. The next irregularity centered on what Loeb called forward-directed jetting. Fine-tuned positional tracking of 3I/Atlas relative to fixed stars indicated minor shifts from expected gravity-only motion. Such extra gravitational forces often occur in comets, stemming from gas bursts from the spinning core that function like miniature thrusters, gently diverting the path from projections. However, the thrust vector for 3I/Atlas didn't match the expected opposition to the Sun, the spot of peak warming and evaporation. Rather, it seemed aimed ahead, like an invisible force propelling the comet forward in its course instead of sideways. This is significant since routine solar-driven venting should generate pushes largely at right angles to the sun-object axis, given the core's spin and jets activating from diverse spots as they face the light. A forward bias is tougher to account for organically, demanding precise setups of spin direction and jet positions that come across as forced. Loeb floated the idea that this could hint at deliberate maneuvering, a bold assertion without solid proof, but in line with his openness to artificial provenance ideas. The third peculiarity touched on luminosity and effective area. 3I/Atlas seemed unusually bright. The comet's luminosity turned out stronger than anticipated for an object of its projected dimensions, hinting that the core might be bigger than first estimated, its reflectivity greater than that of average comets, or the dust envelope's light diffusion more effective than usual. Lowe pointed out that such luminosity irregularities often stem from positional factors. For instance, a disc-shaped structure, akin to a sail, bounces back more illumination than a spherical body of similar weight, or specialized surface layers could boost reflectance. He refrained from asserting this indicated human-made origins, but stressed that luminosity surpassing forecasts requires accounting, particularly alongside further peculiarities. The fourth irregularity concerned the path's alignment. 3-2 Atlas's path schemes remarkably near the solar system's orbital plane, where planets circle the sun, in contrast to earlier interstellar intruders. Oumuamua entered from nearly at right angles to that plane, as did 2I/Borisov, aligning with haphazard entry from arbitrary cosmic directions. 3-2 Atlas's near-planar route proves statistically rarer under pure randomness, although not entirely unlikely. Lowe proposed this could signal an intentional approach, with the object's course purposefully set to traverse the zone rich in planets and possible advanced societies. We can now evaluate how the XMR imagery ties into these irregularities. The absence of a detectable tail solidly backs Lowe's initial finding, bolstering his timely alerts that 3-2 Atlas deviated from standard comet patterns. The dust envelope's tight, balanced form matches subdued or missing gas emissions, fitting the second irregularity regarding atypical motion directions. The core's indistinct outline blocks a clear check on the luminosity issue. Yet the envelope's dim glow, even with expected vigorous outbursts, reinforces the notion that this entity's illumination generation or diffusion strays from typical comet norms. Importantly, alignment across these irregularities doesn't confirm artificial construction. Plenty of ordinary causes could explain each deviation. No tail might stem from viewing angles or minimal output. Motion ahead could arise from particular spin setups. Luminosity might trace to differing reflectivity or particle traits. Path alignment could just be coincidence. After all, with merely 3 interstellar objects spotted so far, we lack grounds for robust probabilistic assertions on common paths. The astronomical community's response to Lowe's views has been firm yet courteous. Many experts recognize the deviations, but lean toward mundane interpretations. They highlight how subtle tails might evade detection due to viewing constraints, weak contrasts below sensing limits, interference from distant stars or galaxies, or sporadic appearances. They underscore that atypical traits aren't unattainable, as the cosmos routinely yields unexpected setups without needing intelligent design. This clash between widespread curiosity and expert restraint fosters a compelling interplay. Audiences, fueled by years of speculative fiction and fresh buzz around Oumuamua, crave signs of otherworldly visitors. Each deviation fuels talk of alien devices or relics. Experts, drilled to explore everyday causes before extraordinary ones, downplay the weight of such hints. They point to noisy data, tricky biases, and sparse observations unfit for solid judgments. Lowe holds a distinctive spot in this exchange. His qualifications command respect: Harvard faculty, scores of vetted studies, past leadership in the astronomy division. Yet he ventures public conjectures that colleagues typically shun. His online essays and media spots deliver the exploratory scenarios that formal outlets sidestep, the hypothetical tales that captivate general interest. Detractors label him as fame-hungry, tarnishing the field's image by validating outlier theories. Backers hail him for probing taboo topics, broadening acceptable discourse, and fostering curiosity. Lowe's engagement with 3-2 Atlas stands out because his prior cautions now seem prophetic. He urged monitoring for missing tails. XMR verified it. He flagged luminosity quirks. The blurry core and pale envelope sustained the enigma. He floated acceleration not powered by sunlight. Positioning studies stay inconclusive. Whether these validations redeem his doubts on routine causes or merely showcase sharp foresight hinges on one's stance toward bold assertions needing bold proof. Upcoming parts will probe further into the observations Low emphasized: spectral scans uncovering compositional quirks, polarization defying usual frameworks. Each dataset enriches the puzzle, potentially clarifying deviations via routine processes or weaving them into a tapestry calling for deeper scrutiny. The question isn't simply if 3i/Atlas appears odd, it undoubtedly does, but whether that oddity stems from unfamiliar natural variety or something truly outside our existing models for interpreting interstellar objects. As the ESA's imagery demonstrated, the most significant insights often lie not in what's visible, but in what's notably absent. Imagine a comet tail that's expected yet missing, or an intruder that seems nearly familiar, yet somehow off, or a fragment of the cosmic jigsaw that refuses to slot in, no matter the force applied. Part 6. Insights from Spectra and Makeup. Chemical analysis uncovers narratives that visuals by themselves can't disclose. In September 2025, when the James Webb Space Telescope directed its near-infrared spectrograph toward 3i/Atlas, the focus wasn't on tails or cores. Instead, it parsed light, splitting arriving photons into their spectral components to detect the molecules lurking in the coma and their relative abundances. Spectroscopy stands as astronomy's premier analytical method, decoding details like temperature, makeup, speed, and even magnetic intensity through the telltale bright lines of emission and dark bands of absorption across the full electromagnetic range. JWST's discoveries quickly drew scrutiny. Carbon dioxide overwhelmed the coma's emissions, outpacing water vapor by a factor of 8. To put this in perspective, ordinary comets in our solar system display the reverse pattern. Water vapor typically leads, making up 60 to 80% of the sublimating gases, while carbon dioxide and carbon monoxide follow as lesser components. This reversal is rare, though not entirely novel. A few solar system comets exhibit carbon-heavy profiles, especially those from the remote Oort cloud, where assembly conditions varied from the hotter zones nearer the center where the majority formed. Yet 3i/Atlas hails from beyond our system. It's interstellar, born in some distant star's planetary realm under possibly starkly altered circumstances. The prevalence of carbon dioxide might echo the chemistry of its origin environment. A star with altered metal content, shifted carbon-to-oxygen balances in its protoplanetary disk, or unique thermal regimes in the region where comets took shape. On the other hand, it might signal selective depletion of water over the eons 3i/Atlas drifted through interstellar voids, where cosmic rays and UV radiation from far-off stars gradually altered its surface frosts, severing bonds and letting volatile water flee while sturdier carbon dioxide lingered. The spectral data also hinted at faint traces of additional compounds, carbon monoxide, maybe methane in small amounts, and subtle suggestions of intricate organic materials. These signals hovered near the detection threshold, demanding meticulous review to separate genuine signals from equipment noise or interference from nearby objects. Still, if verified, they would sketch a scene of rich chemical diversity, an entity bearing not only basic frozen gases, but possibly prebiotic substances, organic structures that elsewhere could act as precursors to biology. The spectral traces of dust introduced further enigma. Sunlight bouncing off particles in the coma displayed an atypical reddish tilt, with longer wavelengths reflected more readily than shorter ones, shifting the overall hue toward the red spectrum. Comets within our solar system generally exhibit even or neutral tilts, their grains scattering light fairly consistently over visible colors. This reddish bias points to either peculiar dust makeup, perhaps grains laden with carbon, organic remnants, or iron-infused minerals, or atypical particle dimensions, where bigger chunks alter scattering compared to the micron-fine dust common in standard comet views. Polarimetry layered on even more intrigue. This technique gauges light's polarization as it ricochets from dust particles, with the extent and orientation disclosing clues about particle form, scale, and constituents. A European team performed polarimetric observations of 3i/Atlas via multiple mid-sized scopes, monitoring shifts in polarization relative to the phase angle, the geometry linking sun, comet, and viewer as the object traversed its path. The outcomes prove compelling. 3I/Atlas displayed a pronounced negative polarization dip at low phase angles, dipping to -2.7% near 17 degrees. In simpler terms, this denotes a distinct scattering pattern. At those orientations, sunlight polarizes orthogonal to the scattering plane, unlike the parallel alignment usual in most cases. The severity of this negative dip, its deepest point, and the turnaround angle where it flips to positive both yield key insights into dust traits. Typical solar system comets register negative branches of about -1 to -1.5%. 3I/Atlas's -2.7% far surpasses that, hinting unconventional dust characteristics deviate from standard distributions. Scientific theories connect profound negative polarization features to extremely porous, fluffy particle clusters. These dust particles consist of minuscule subunits held together loosely, riddled with empty spaces and cavities that amplify particular light-scattering effects. On the other hand, the atypical polarization might stem from variations in makeup, such as uncommon silicate blends unlike those in solar system dust, or organic layers that modify how light reflects off the surface. Integrating spectral analysis with polarization data reveals an entity that's both chemically and structurally unique compared to ordinary comets. The prevalence of carbon dioxide implies it formed in an alternative setting or underwent distinct processes divergent from those shaping solar system comets. The atypical dust, with its reddish spectral slope and intense polarization, points to either rare material types or peculiar formations that challenge our long-established knowledge derived from extensive observations of solar system comets. Certain researchers argue these traits merely echo an interstellar background. In truth, detailed examinations of just 3 interstellar bodies leave us with an insufficient dataset to define what's typical for ejecta from alien planetary setups. It's possible that each interstellar arrival exhibits chemical profiles and dust traits that stray from solar system standards, mirroring the vast array of stellar birthplaces, protoplanetary disk makeups, and developmental paths throughout the galaxy. If 2I/Atlas appears odd, it could be due to our narrow perspective, confined to the remnants around a single star. Yet a provocative hypothesis persists, undeterred by repeated natural accounts. Suppose the peculiar dust stands out because it's artificially created? Imagine if those polarization traits arise not from innate mineral fragments, but from fabricated components? Envision carbon-based compounds, custom-built clusters, or specialized reflective surfaces tailored for precise optical responses. This remains sheer conjecture, lacking any concrete proof, yet it hovers in the gap between observations and analysis, prompting uneasy inquiries into detecting engineered substances upon discovery. The confirmed spectroscopic signs of organic compounds, should they hold, stoke further intrigue. Organic substances abound in cosmic settings. Amino acids appear in meteorites. Elaborate carbon chains show up in interstellar nebulae. Building blocks for life have turned up on comets and asteroids across the solar system. Their occurrence on 2I/Atlas wouldn't shock, but it would intrigue deeply, particularly if the suite of molecules diverges from solar system versions, hinting at alternate formation routes, varied chemical milieus, or, though a vast stretch, origins tied to biology if the body traversed a life-bearing system. The dust enigma ties straight into the puzzle of the absent tail. Should the grains be exceptionally sizable or exhibit odd light-handling qualities, they could fail to disperse light effectively in the tail zone, making it undetectable even if material exists there. Or, if hefty particles drive the dust output, those chunks might plummet back toward the core under its feeble pull instead of getting pushed outward by sunlight's pressure to form a tail. No tail emerges not from lack of vaporization, but because the ejected dust stays bound by the nucleus's gravity. This straightforward rationale fits neatly and seems credible. It demands no fringe physics or human-like meddling, merely atypical yet feasible particle traits. Numerous experts endorse this view, regarding it as the most straightforward fix for the tail's non-appearance and the polarization quirks. Still, straightforwardness doesn't equate to certainty. The piling up of these odd yet allowable aspects, CO2 prevalence, reddish dust tilt, strong polarization, absent tail, anomalous speed-up, breeds an eerie aura of peculiarity beyond mere chance fluctuations. The makeup of 2I/Atlas could unveil its origins, providing insights into the stellar surroundings that birthed it. Fresh simulation studies, to be delved into further ahead, propose that 2I/Atlas hails from the Milky Way's thick disk, a venerable, low-metal group of stars circling the galaxy's hub in a swollen layer extending above and below the slim disk housing our Sun. These thick disk stars emerged 8 to 12 billion years back amid a prior chapter of galactic evolution, when the interstellar gas boasted altered elemental mixes, scarcer heavy metals, and distinct molecular profiles. Should 2I/Atlas indeed spring from a thick disk progenitor, its quirky composition aligns logically. Low metallicity zones yield altered mineral buildup patterns, varied ice formulations, and unique organic assortments relative to the metal-abundant locale that birthed our solar system 6 billion years past. The carbon dioxide supremacy, the composition of Nance, might stem from development near a carbon-rich star or within a disk where oxygen was mainly bound to silicates instead of water ice. Such peculiar dust aligns perfectly with what you'd anticipate from ancient, chemically basic substances altered by billions of years under cosmic ray exposure. This backdrop transforms 3I/Atlas from a mere oddity into a valuable asset. Should it truly hold preserved chemistry from the dense disk, it represents a direct glimpse into galactic states from bygone eras, conditions we can typically explore only via indirect views of far-off stars and old stellar groups. Lab examinations of retrieved samples, an ambition well out of reach today, but possibly attainable in coming decades, might uncover isotopic compositions, mineral formations, and organic compounds that narrate the galaxy's early days. Insights into chemical processes that functioned prior to the cosmos being infused with supernova remnants across numerous star generations. Yet currently, we're confined to distant probing, relying on spectroscopy, polarimetry, and imagery from vast distances in millions of kilometers. These methods have uncovered an entity that resists neat classifications, piling up peculiarities quicker than theories can catch up, teasing us with suggestions of rare chemical traits, yet denying clear resolutions. Upcoming data from JUICE, terrestrial scopes as 3I/Atlas nears perihelion, and ongoing efforts with Hubble and Webb could either clarify these enigmas via steady evidence gathering or amplify them by verifying that indeed, this body is as bizarre as it appears. And no, we lack a complete grasp of the reasons. Part 7. Rotation, light curve, dust emission, and the absent tail. Celestial bodies seldom remain motionless. They rotate, flip, oscillate, and nutate, their spin axes carving intricate routes across fixed space amid shifting internal masses and building external torques. For comets, spin provides key clues. It discloses form, influences vapor release patterns, and dictates how jets nudge the body from its orbital path under gravity. Grasping 3I/Atlas's spin turned into a key focus for global watchers, demanding months of unbroken light measurements as it traversed its path, tracking luminosity shifts that hold clues to its turning. A team headed from Spain released the initial in-depth spin study in late October 2025. Their findings drew from various sites across longitudes, ensuring non-stop monitoring as our planet turned, avoiding breaks that could muddle cycle calculations. The light curve, luminosity graphed over time, displayed a distinct 16-hour cycle with swings of roughly 0.3 magnitudes. Simply put, 3I/Atlas finishes a full turn every 16 hours, and its glow fluctuates by about 30% from peak to trough in each cycle. This swing offers hints about its outline. An ideal orb would exhibit zero luminosity, change no matter the spin, since every angle appears the same. Stretched forms display luminosity shifts as their projected area alters with turning, sometimes showing their wide face, other times their slim edge to the viewer. The 0.3 magnitude swing points to moderate stretching, maybe ratios near 1:3:1, not extreme, unlike Oumuamua's guessed 10:1 cigar form, but clearly not round. The spin duration itself is typical for comets. Those in our system range from hours to days, with 16 hours right in the average zone. This counters odd ideas like engineered constructs, which could whirl quicker to mimic gravity or stay steady via control tech. 3i/Atlas flips like any natural item would, following angular momentum rules and tweaks from vapor jets that gradually adjust its spin. Yet the light curve conceals further intricacies. A nearer look spots faint strays from ideal sinusoidal patterns, suggestions of a backup cycle, potential glow shifts unrelated to spin, sporadic abrupt spikes possibly signaling isolated vapor bursts. These irregularities hover at the edge of detectability, needing meticulous review to separate true signals from issues like air turbulence, device biases, or stray stars overlapping 3i/Atlas in the frames. Should they hold up, such irregularities would show that 3i/Atlas isn't just a passive chunk turning steadily. Rather, it's releasing gas dynamically, tied to its spin, maybe via targeted jets firing when certain areas face the sun, or through landforms, cliffs, craters, cracks, sparking uneven melting spots. This fits seamlessly with standard comet actions. Probes like Rosetta have shown comet cores as rugged worlds with diverse landscapes yielding changeable, location-based gas outflows. Dust production forecasts bring an extra layer to this mystery. Through examining the light bouncing off the coma and matching it against simulations of how efficiently dust scatters, scientists calculated that 3i/Atlas was shedding mass at levels ranging from 0.3 to 4.2 kilograms per second. That's modest when set against standard comets nearing the sun. Vibrant, energetic comets might lose hundreds of kilograms each second or even tons at their closest solar approach, generating stunning tails that anyone can spot without aid. The restrained output from 3i/Atlas hints at either subdued activity, limited vaporization due to a volatile poor core, or outgassing that fails to drag much dust along. The gap between gas release and dust output is revealing. Spectral analysis verifies the presence of gas. CO2 leads the mix. H2O shows up too. Traces of other volatiles emerge. Yet the dust that gas pressure ought to hoist into the mix stays mostly missing from the tail area. How can gas vent out without hauling dust with it? A few processes might account for this mismatch. One option relates to particle dimensions. Should the dust grains mostly be sizable, on the millimeter scale instead of microns, they'd prove too hefty for gas flow to propel them past the nucleus's getaway speed. They might rise for a moment, linger, then drop back down, without ever breaking free to form a tail. This setup would yield a coma packed with hefty grains close to the core, but no stretched-out tail since the bits wouldn't travel far enough for sunlight's push to take over and blow them outward. A different idea centers on stickiness. If the dust grains cling together, maybe covered in organics or zapped with static, they could bunch up right after lifting off, creating clumps too weighty to flee. Such clumping would curb tail development while letting gas flow out unhindered, matching the scene we see: lively coma, missing tail. Sticky dust has turned up on other comets, especially those loaded with organics. So this idea draws from real cases. Yet another factor could be the line of sight. If the dust tail aims straight at or away from our planet, it might look squashed to nothing, tucked along our view. This makes sense in terms of angles, but odds are against it. The paths of orbits rarely line up the tail, sun, and watcher so neatly. Plus, various sites watching from varied perspectives haven't spotted the tail, pointing to it being truly faint or non-existent, not just out of view. The spinning adds chaos to the mix. With the core rotating, fresh areas face the sun in turn, possibly varying in makeup, vapor rates, and how well they snag dust. Suppose only select spots eject dust, and those spots point so the flung material doesn't line up opposite the sun. That could block tail building despite steady action. It calls for particular, but feasible, arrangements of spin axis, jet spots, and sight lines. Past cases offer some echoes, but fall short of full answers. 2i/Borisov, the last interstellar visitor, sprouted a glorious tail clear in backyard scopes, showing such wanderers can act normally. Oumuamua displayed none, even though it swung way nearer the sun than 3i/Atlas, fueling the arguments that Yi and team still wrestle with. 3i/Atlas sits in between, livelier than Oumuamua, duller than Borisov. Yet this in-between spot feels off, like a mean that masks wild swings instead of showing standard patterns. The draw for folks is gut level. Picture a comet whirling steadily, puffing gas outward, dropping dust into its glow, but bulking it sprouting a tail. How does that work? It's akin to a vehicle idling with motor humming, tires turning, yet stuck still because the gearbox jams in park. Every part works as it should, but the payoff, progress here, or tail growth there, just doesn't happen. The split between effort and showy results stirs mental unease that expert breakdowns can't quite soothe. Wild theories of deliberate damping allure, though lack backing, might have made object purposely dialed down its shine, venting barely enough to pass as commentary, while dodging the flashy tail that'd draw eyes. In theory, sure, but for what gain? What edge does blending and offer a craft touring our system? Unless spotting spells risk, maybe advanced societies shun meetings, or cosmic rules ban bold entries. Yet no solid reason for hiding emerges. And if there were, the job looks sloppy, as we've nabbed 3i/Atlas regardless and are picking over its quirks. Most experts lean toward natural causes. Peculiar be permitted characteristics of the grains, paired with relatively low levels of activity, result in a coma lacking any tail. This explanation demands no novel physics, relies on no strange substances or sentience, and aligns seamlessly with the wide variety of cometary behaviors seen among solar system bodies. The sense that it's somehow lacking, the lingering doubts about precisely why these grains possess such traits, do not undermine its validity. Nature has no duty to align with our desires for tidy, graceful theories. Still, excitement mounts as 3i/Atlas nears perihelion, the closest point to the sun, where solar warmth intensifies and activity ought to surge. Should a tail emerge, it would happen right there. Monitoring from JUICE, along with synchronized ground-based efforts and orbital telescopes, will scrutinize the instant when sublimation surpasses a critical level, potentially unveiling the absent tail as it trails the nucleus like a flag billowing in the wind. If that instant arrives, it could unravel a good portion of the enigma. But if it fails to, if 3i/Atlas glides past perihelion without a tail even under peak heating, the oddity will solidify into a puzzle calling for bolder ideas beyond atypical dust or unfortunate observation perspectives. The coming weeks will reveal if 3i/Atlas is just an quirky variant within nature's limits, or truly an outlier challenging our models of celestial rubble. Part 8. Extreme negative polarization and its implications. Light consists of electromagnetic waves vibrating as they travel through space at 300,000 kilometers per second. Sunlight is typically unpolarized, with vibrations happening haphazardly across all planes perpendicular to its path, yielding no favored alignment. However, upon scattering from particles, like dust grains, air molecules, or comet fragments, light can polarize, with vibrations favoring a single direction. Assessing this polarization uncovers details about the scattering agents that other methods overlook, positioning polarimetry as a key tool in astronomical analysis. For 3i/Atlas, polarimetry data uncovered an anomaly. The extent of linear polarization, the share of light that polarizes post-scattering, displayed a pronounced negative dip at low phase angles. Phase angle refers to the Sun-Comet observer configuration, basically the viewing angle for the reflected solar light. Around 17 degrees, 3i/Atlas's polarization hit -2.7%, indicating alignment perpendicular to the scattering plane instead of parallel. While negative polarization often appears at small phase angles in solar system objects, its magnitude is crucial. Typical comets exhibit negative values of about -1 to -1.5%, with rare exceptions dipping to -2%. At -2.7%, 3i/Atlas stands at the fringe of recorded data, hinting at dust traits far removed from the usual. The inversion point, where polarization shifts from negative to positive with rising phase angle, sat at roughly 17 to 18 degrees, a bit off from the standard 20 to 25 degrees for most comets. Physically, what does this signify? Polarization models are intricate, drawing on Mies scattering for round particles and more elaborate simulations for jagged forms, plus the interplay of waves with a material's optical traits. Yet the core idea is that negative polarization at low phase angles stems from repeated scattering and coherent backscattering, where rays bounce multiple times inside spongy clusters before emerging. A steeper negative dip signals greater efficiency in this mechanism, often linked to extremely porous, fluffy dust particles, one's mostly empty space with fractal-like builds, where minuscule bits loosely bond. Lab tests on comet-like simulants aid in decoding such findings. Scientists craft artificial dust blends of silicates, organics, and ices, then gauge their polarization under lab conditions. Aggregates with porosity over 90%, that's 90% empty, 10% matter, generate deep negative dips akin to those in 3I/Atlas. These formations are delicate, prone to breaking under impacts or pressure, yet they endure in space's mild setting, with slow speeds and infrequent clashes. Other views suggest atypical makeup over odd shapes. Some substances, like carbon-heavy organics or particular silicate combos, may scatter light with polarization curves unlike standard solar system silicates. If 3I/Atlas's grains boast an exotic chemistry, tied to its interstellar roots and origins in a dense disk with altered element ratios, the polarization quirk might stem from ingredients, not just porosity. Another angle involves coatings on surfaces. Grains could feature core mantle setup structures featuring mantles around silicate cores, or the reverse with organic layers dominating the scattering of light, represent such configurations. These setups can generate atypical polarization patterns without needing drastic alterations in porosity or overall makeup. In the solar system, coatings frequently appear on dust particles, arising from gas condensing on chilly grain exteriors or from high-energy processes that modify outer layers. Linking this polarization to the absent tail demands some conceptual contortions, yet viable routes emerge. Grains with exceptional porosity and fluffiness could exhibit reduced terminal speeds within the coma. Instead of being swiftly propelled by gaseous drag, they would meander gradually from the nucleus. This scenario might yield a confined coma, with particles hovering close to the core instead of flowing outward to form a tail. Moreover, such fluffy clusters could break apart under solar radiation pressure or electrostatic influences, splintering into tinier fragments that scatter light with lower efficiency, thus making any tail optically dim despite its physical existence. Speculating on synthetic substances is unavoidable, though it's tightly bounded by evidence. Might fabricated particles yield intense negative polarization? In theory, certainly. Think carbon nanotubes, graphene layers, or metamaterials engineered for specific optical traits. Such elements could manipulate light in unconventional manners. However, positing artificial substances necessitates accounting for why an engineered entity would replicate the polarization of natural dust, select this particular scattering profile, and pursue such imitation. Absent a clear rationale or process, this idea remains intriguing yet scientifically barren without backing data. The polarimetry findings bolster the array of oddities surrounding 3I/Atlas. They offer yet another metric that positions this body at the outlier fringe of cometary norms. This extra evidence implies the object stands out, even among the varied comets we've examined. Whether that distinctiveness stems from inherent natural variation stays under debate. Interstellar visitors draw from distinct birth settings and may inherently diverge from solar system comets, or perhaps signal something rarer, remains a point of contention. Certain scientists warn against reading too much into isolated readings. Polarimetry poses difficulties, demanding meticulous calibration, thorough grasp of instrument biases, and adjustments for atmospheric influences that might spuriously induce polarization. The 3I/Atlas observations push the boundaries of what's practical. Given the target's dimness, reported error margins on polarization might undervalue hidden systematics. Additional data boasting superior signal-to-noise ratios could reveal milder extremes, pulling 3I/Atlas into typical ranges, but the current figures hold as stated, and several separate sightings yield matching outcomes, indicating the profound negative polarization is genuine, not an error. Assuming it's authentic, it calls for accounting via spongy dust forms, rare makeups, or processes we haven't fully explored. Upcoming studies, especially from JUICE leveraging its polarization tools, could sharpen these assessments, validating or dismissing the outlier readings and aiding in separating rival theories. The dust enigma lies at the heart of decoding 3I/Atlas's essence. Does this body merely represent a comet with atypical particle traits from its interstellar origins? Or does the dust hint at profound enigmas? It could involve relic substances from the galactic thick disk, or clumps rich in organics bearing prebiotic compounds. Or maybe concepts beyond our current scope, constrained by solar system precedents. Polarization snapshots suggest resolutions, yet foster vagueness, enriching the enigma without clarifying it. Akin to a crossword hint matching several terms alike, it compels gathering more clues before boldly completing the entry. Part N. Alternative ideas, unconventional notions. Anomalies invite diverse interpretations, and 3I/Atlas has gathered sufficient peculiarities to fuel a full spectrum of theories, from routine to outlandish. Science insists on depleting ordinary accounts before entertaining the exceptional. Thus, we'll first inventory standard options, then tentatively step into bolder realms. The simplest everyday rationale for the unseen tail centers on observational alignment. Should the tail align straight toward or from Earth, along our sight line? Foreshortening would render it undetectable, squeezed to a dot instead of spanning the sky. Geometrically sound and free of odd physics, this notion encounters hurdles. Observations from various sites over weeks ought to yield diverse perspectives, but none spotted evident tail stretching. The arrangement of the geometry would have to be improbably coordinated over various observational periods, which challenges statistical plausibility. Another straightforward rationale points to reduced dust generation. Should 3I/Atlas release gas while generating only scant dust, possibly due to a makeup devoid of small particles or surface layers that block dust from being carried away? The tail might primarily consist of ions instead of dust particles. Ion tails tend to be dimmer and are mostly detectable in ultraviolet spectra, where glowing ionized compounds shine, often overlooked in optical surveys. This scenario matches the spectral evidence of gas, and the imaging results lacking a clear tail, yet it falls short in accounting for the sharp drop in dust output relative to gas, particularly for a body that's actively venting carbon dioxide. A further idea highlights atypical dust characteristics, such as oversized particles, elevated porosity, or cohesive clumps that settle back onto the core instead of streaming into the tail. As we've covered before, this remains the leading theory among experts. It demands no unconventional physics, slots into the range of known comet behaviors, and dovetails with polarimetric hints of porous grains. The absent tail thus stems from dust behavior rather than a lack of sublimation. The prevalence of carbon dioxide adds yet another perspective. Ice turning to vapor from water is effective at picking up dust, thanks to its high sublimation heat, which fuels strong gas streams that sweep particles along. In contrast, carbon dioxide's per molecule sublimation energy is milder, yielding gentler outflows that could raise dust with less success. If 3I/Atlas mainly features carbon dioxide ice alongside little water, dust lifting might be limited despite robust sublimation, resulting in emissions heavy on gas but light on dust. A sixth option involves particle reflectivity. Should the dust consist of unusually opaque grains, like carbon-rich organics or iron-laden silicates, they'd reflect minimal sunlight, even if abundant. Physically, the tail could be there, yet optically undetectable, concealed by its failure to gleam against the starry backdrop. This notion clashes with sightings that do pick up coma dust, implying the grains aren't wholly non-reflective. Still, the coma material might vary from tail stuff in scale or makeup. When conventional ideas falter, unconventional ones emerge. The mildest of these unconventional views casts 3I/Atlas as an intermediate body, not quite a comet nor a full asteroid, maybe a piece of a bigger entity altered by heat inside or a crash, yielding odd volatile patterns and dust traits. Such hybrids could lurk in solar system groups, dwelling in the fuzzy divide between comets and asteroids, complicating any tidy labels. More daring is the notion of an engineered artifact. If 3i/Atlas were a built item, a sensor craft, abandoned vessel, or snippet of a solar sail, it could vent from leftover volatiles built up during eons of space journeying, sans the dust-laden tail typical of comets. A designed exterior might curb dust release on purpose to shield gear from grit or shrink its radar signature for concealment. The carbon dioxide surplus might stem from deliberate fuel selection or unintended frost from cosmic carbon dioxide on its shell. This idea draws quick pushback. What about hints of structured shapes? Man-made things favor linear borders, sharp corners, and repeatable build elements absent in 3i/Atlas's fuzzy pics. What about fabric clues? Alloys, plastics, synthetics ought to yield unique spectral or polarization marks unlike stone and frost. But data points to blends akin to everyday rocks and organics. What about odd motions? Made objects could show steered tilts, thrust bursts, or radio signals. None found. Loeb's solar sail idea, first floated for Oumuamua and now repurposed for 3i/Atlas, suggests a slim mirrored sheet pushed by sunlight. The noted forward push in position data might come from that pressure if the thing's planar and angled right. The tail's absence makes sense too. Sails lack tails barring volatile coatings that vaporize, and even those would form tails unlike standard comet ones. The spotted carbon dioxide could arise from frost gathered on the sail across interstellar voids, now melting under solar warmth. Yet the sail theory grapples with rotation. Sunlight pressure on sails would twist them into fast spins without ideal balance or onboard fixes. 3i/Atlas's 16-hour the tumbling motion observed in its rotation indicates a lack of any stabilizing forces, implying an organic, uneven form rolling through space while adhering to the rules of angular momentum preservation. Moreover, the center of mass's round uniformity clashes with the irregular venting one would anticipate from a solar sail, where one side would be unevenly warmed by sunlight, leading to lopsided gas emissions. A more unconventional option could be a hibernating comet that's beginning to stir again. Imagine 3i/Atlas having drifted for eons across the void between stars, its outer layers stripped of easy-to-vaporize materials by relentless cosmic radiation, creating a hard shell that blocks out gassing. Now, as it ventures into the warmer reaches near our sun, the increasing heat gradually cracks this barrier, permitting some vapor to seep out, though not forcefully enough to kick up particles yet. A tail could emerge soon as the outbursts intensify, suggesting we're catching this wanderer mid-shift from quiet slumber to lively outburst. It's worth touching on the panspermia hypothesis too. Suppose 3i/Atlas hails from a star system teeming with life. Might it transport living remnants, like seeds, inactive bacteria, or compounds forged by biological means? Spectroscopic hints of odd carbon-based traces could point to origins tied to life. Yet, teasing apart life made from lifeless organics from afar remains incredibly tough. Supporters of panspermia argue that microbes hitchhiking on hurled comets across the cosmos makes energetic sense. A tiny portion of such flung debris could settle on life-friendly worlds, with some hardy life forms enduring the trip encased in frost. In this view, 3i/Atlas might serve as a vessel, ferrying microbial envoys from distant realms. But this stacks guesswork atop guesswork. We're unsure if those carbon signals are truly odd. We can't confirm if they're from life. Today's tools can't probe for life markers at a distance anyway. Still, the notion excites because it elevates 3i/Atlas from oddity to perhaps humanity's grandest breakthrough. Solid proof of alien biology, even tiny bugs, even extinct, arriving in our cosmic neighborhood through everyday mechanics. Ties to popular media are unavoidable. Arthur C. Clarke's Rama, that tube-shaped extraterrestrial relic slipping into the solar system, posing as a rock, fired up minds long ago. The legend of the Black Knight orbiter, an alleged man-made thing circling Earth, lingers on despite refutations. All quirky sky sightings get sifted through such stories. Societal frameworks push us to see the weird as engineered. 3i/Atlas slots right in, enigmatic, offbeat, defying simple answers, ideal for overlaying our dreams, dreads, and genre-inspired visions. The central puzzle piercing the hype is ESA's rush to act. Redirecting juice, spotlighting the surprise factor in press releases, rushing out early findings. All point to agency-level acknowledgement that 3i/Atlas matters more than your average comet watch. Does ESA hold back some undisclosed intel? Have their private reviews uncovered extra quirks not in the reports? Or is the haste just smart opportunism? After all, cosmic drifters like this won't linger for red tape. They demand study while in range. Openness in research counters secret stunners. Big reveals usually slip out via talks, draft papers, offhand chats before formal drops. If ESA spotted blatant signs of tech, structured shapes, broadcasts, bizarre substances, word would spread, and online buzz would outpace any press event. No such chatter means probably no clear proof, merely a buildup of suggestive oddities that together merit focus without any single one sealing the deal. The real hurdle in knowing is spotting when quirks shift from random chatter to meaningful clues. A single outlier sparks interest. A pair could be chance. 3 perks up notice. 4 or 5 on one item start looking deliberate. 3i/Atlas piles up a set. No tail, CO2 lead, quirky light scattering, unexplained push forward, reddish particle curve. Each open to everyday causes alone, but together they stir discomfort. When does weird yet explainable tip into time to weigh wilder ideas? Research lacks a set line, just a built-in caution that shuns far-out theories until evidence demands them. That demand hasn't struck for 3i/Atlas so far, and it might never. Upcoming data could clear it all up routinely. Tail sprouting at closest solar approach, particle traits accounting for the scattering, proof that CO2-rich thick disk comets just act unlike our assumptions. The enigma would dissolve, giving way to richer insights into comet variety and traits of star-crossing visitors. Scientific progress typically unfolds in small steps. One more observation logged in the records. One additional insight into the ingenuity of the universe. Alternatively, the oddities could linger, defying straightforward explanations and compelling us to broaden our conceptual models for interstellar objects to incorporate ideas we've scarcely explored. Such broadening wouldn't automatically imply extraterrestrial origins. It might instead point to novel mechanisms of particle clumping in dust, unforeseen reaction routes in long-ago star systems, or motion patterns we've overlooked due to unfamiliar circumstances. Yet it would require us to admit that paradigms derived from our solar neighborhood could be insufficient or downright deceptive when extrapolated to visitors from afar. Herein rests the true worth of these cosmic travelers, not as possible relics, but as educators, urging us to grapple with the boundaries of our expertise and enrich our grasp of the galaxy's varied phenomena. The core issue isn't if 3i/Atlas is organic or engineered. Rather, it's whether we possess the mental agility to identify emerging forms of natural phenomena upon their arrival, or if we'll stay confined by rigid binaries that constrain instead of freeing our perspectives. Part 10. Concealed perspectives, conflicts, and warning signs. Scientific inquiry seldom follows a seamless route from detection to comprehension. Instead, it often navigates a labyrinth of inconsistencies, unclear readings, and discussions where experts draw varied inferences from the exact same evidence. 3i/Atlas captures this chaotic essence, offering a web of observations that resist fitting into a tidy story. Let's delve into the particular conflicts that render this entity both exasperating and captivating to the same degree. To start, consider the issue with the luminosity profile. Initial calculations, drawing from visual brightness and estimated range, indicated that 3i/Atlas's core could span several kilometers, rendering it dynamically influential and hefty enough to hold onto ample frozen materials. However, the XMR snapshot revealed a blurry core without clear resolution, implying it might be far tinier, possibly just a few hundred meters wide. How can we harmonize the intense observed glow with such a modest scale? Possibilities include an unusually reflective surface compared to standard comets, capturing greater light relative to its extent, an outsized role from the surrounding haze in overall illumination, or flawed preliminary assessments stemming from shaky premises about how dust disperses light. This is crucial since dimensions dictate heft. Heft influences gravitational cohesion. which in turn governs if gas release can meaningfully shift the path. Lighter bodies undergo stronger nudges from equivalent venting intensities than bulkier ones. Should 3I/Atlas prove compact, the detected non-gravitational pulls align more readily with routine processes. If substantial, they necessitate intense or uneven emissions to account for the path deviations. Next, conflicts arise in the propulsion readings. Various analysts scrutinizing identical positional records arrive at divergent views on the strength and orientation of extragravitational influences. Certain studies detect thrust aligned with the sunward direction, echoing Eloy's assertions. Others spot shifts orthogonal to the solar alignment, matching common comet stream activity. A further group contends that observational margins are so wide that any purported signals are at most tentative, likely stemming from procedural flaws in locating the object or aligning reference stars. Such disputes are commonplace in tracking asteroids and comets. Gauging minute thrusts demands exceptional accuracy and minimal biases. Effects like air distortion, flawed scope following, or discrepancies in stellar maps can mimic authentic dynamics. Resolution awaits extended monitoring over greater periods, enabling path computations that smooth out noise and expose true orbital traits. Until then, doubt prevails, and assertions of atypical motion stay disputed. Finally, the indistinct core fosters profound vagueness. We lack details on 3I/Atlas's form, exterior traits, spin rate, tilt, or precise makeup. What's visible is merely the haze, that diffuse sheath potentially concealing diverse core setups. Does the core stretch like Kummu'a, or sit more as a rounded blob? Is it a solid chunk or a fragile aggregate bound by faint pull? Might it bear terrain marks, pits, escarpments, sprays, or remain sleek and plain? These gaps ripple into all evaluations, obliging experts to rely on guesses that could be profoundly off base. Instrumental hurdles heighten this murkiness. 3I/Atlas dims quickly, necessitating prolonged captures that build interference and hinder isolating the backdrop. Its velocity calls for pursuit imaging that risks smearing or insists on advanced compositing techniques. Observing it poses challenges due to its remoteness. Discerning fine particulars demands top-tier equipment pushed to their extremes. Even advanced scopes like Hubble and JWST grapple with such dim and swift targets, yielding photos and spectral data where signal-to-noise levels hover just beyond bare detectability. Selection effects warrant attention too. Our recent encounters have conditioned us to spot oddities in visitors from beyond our system. Oumuamua's peculiarities primed us to anticipate quirks in later arrivals. Any departure from standard comet-like actions draws outsized scrutiny, endless chatter, and arguments, whereas routine traits get a quick mention before fading from view. That said, these oddities aren't fabrications. They stem from genuine readings. Yet our lens of anticipation may inflate their import past what the raw figures justify. Warning signs pile up when several unrelated quirks surface in one entity. Taken alone, each finds a ready rationale. Preeminence of carbon dioxide, origins outside our solar neighborhood, absent tail, shape or particle dimensions, atypical polarization, fluffy particles, unusual forward thrust, uneven gas release. But crafting accounts that tie them all together coherently proves tougher. You'd require a framework featuring CO2's lead role, generating vapor streams that poorly carry along particles, fostering clumpy formations via targeted clumping mechanisms, syncing with emission designs that drive that non-gravitational push. Every link holds water individually, but the full picture starts to seem forced. Here's where Bayesian logic enters the picture. In this approach, you refine odds using piling proof. A lone quirk nudges chances toward unconventional origins just a bit. Several build on each other, each nudge widening the shift. Still, pinpointing the tipping threshold remains a matter of judgment. Eventually, the gathered proof renders outlandish ideas viable rivals to everyday ones. Not via any lone datum clinching the oddball origin, but because standard accounts strain to encompass the full set at once. Detractors contend this exact juncture invites prejudice. Beginning with slim odds for engineered provenance, which most experts do, citing the scarcity of advanced societies across the universe, means even clustered quirks barely budge those odds. Natural accounts retain the edge, thanks to the heavy tilt of initial assumptions. Shifts toward artificial or rare natural scenarios only grow notable if your starting odds already lean that way. Clashes between popular and expert views fuel these disputes. Media blasts alien-esque comet or puzzling body stump stargazers, fostering a sense of widespread bewilderment amid what's actually vigorous, routine scholarly exchange. Experts wince at such coverage, watching their nuanced qualifiers and doubts morph into hype. Meanwhile, the wider audience, eager for stellar drama and weary of possible extraterrestrials, likely not tales, seizes on these quirks as clues that at last, we've snagged true enigma. ESA's measured yet attentive stance treads a balanced path. The organization highlights the surprises, startling to all, sans backing wild theories. It redirects the JUICE probe, underscoring research value without touting discoveries. It shares visuals and findings swiftly, upholding openness minus hasty verdicts. Such rigor comforts, yet irks those seeking straightforward verdicts. Does 3i/Atlas verge on bizarre, or just atypical? Does it merit the stir, or are we inflating instrument glitches and bias? Lingering puzzles grow with ongoing scrutiny. Might a tail appear post-closest solar approach, under peak warmth? Could JUICE sharpen the core's image or better map the envelope? Might spectral analysis uncover fresh chemical twists? Say, isotope signatures hinting at primordial star settings? Or unfamiliar compounds absent from local icy wanderers? Could polarization studies hone particle traits, tightening viable makeup and forms? Will extended tracking clarify the thrust question, separating true dynamics from observational errors? Any of these probes might normalize 3i/Atlas, slotting it into familiar bins with minor asides on its quirky yet accountable traits. Or they might intensify the riddle, validating quirks, unearthing more, edging it from easy rationales. Research flourishes amid such ambiguity, in the fruitful clash of findings against frameworks, sightings against principles. Yet audiences and certain researchers yearn for closure, the ease of certainty, the solace of tidy labels. What unfolds before us is science at its vibrant core. In its raw state, science unfolds as a tangled, tentative process, riddled with disputes, candid about its gaps in knowledge. This approach feels more robust than feigned assurance, truer to reality than rushed agreement, yet it stirs unease, stranding us amid options without proclaiming triumph for any theory. The saga of 3i/Atlas instills restraint and modesty amid intricate puzzles. It honors the challenge of sifting facts from limited, cluttered, vague observations gathered over vast cosmic distances. Those cautionary signals aren't alerts of peril, but signposts for uncharted realms, areas where our charts fall short and our insights remain tentative. Venturing into such spaces demands boldness to hypothesize, tempered by rigor that insists on proof. Creativity to ponder wild scenarios, offset by doubt that guards against fantasy posing as breakthrough. Part 11. Backstory. Bulky layer as primordial cosmic cradle. Each celestial body holds its genesis tale inscribed in its makeup, form, and motion. For 3i/Atlas, that narrative starts far from our stellar locale, in the distant folds of the Milky Way's thick disk, a cluster of stars born in the galaxy's infancy, when the cosmos boasted fewer heavy metals. Fresh simulations tracing 3i/Atlas's path rearward across eons of galactic motion reveal this surprising birthplace, not in the slim disk housing our sun, but in the swollen ring of ancient stars wheeling high and low around the galactic midplane. The thick disk emerged 8 to 12 billion years past, in an era when the Milky Way was compact, turbulent, and elementally distinct from now. Its stars display reduced metallicities, scarcer heavy atoms such as carbon, oxygen, silicon, iron, since the gas clouds birthing them had seen fewer stellar blasts to seed enrichment. These luminaries circle the galaxy's core at brisk speeds at right angles to the plane, their paths slanted and irregular, echoing the fierce upheavals that sculpted the thick disk. Maybe through galaxy collisions, maybe via fervent starbirth in the Milky Way's stormy dawn. Should 3i/Atlas hail from a world orbiting a thick disk sun, its elemental profile clicks into place. Sparse metal settings alter how minerals solidify in nascent planetary rings. The balance of carbon to oxygen fluctuates, influencing if carbon binds into carbon monoxide, carbon dioxide, or carbon-based compounds, or gets snared in silicates or graphite. Icy water might dwindle if oxygen runs low or ties up elsewhere. The prevalence of carbon dioxide we detect could signal birth in a metal-poor, carbon-laden setting, contrasting sharply with our Sun's metal-abundant birth cloud. Reversing the orbital path to trace 3I Atlas's roots demands heavy computation and brims with doubts. You begin with its present spot and speed, gauged by star mapping data. Then run the motion formulas in reverse, factoring in pulls from the Sun, planets, close stars, the galactic layer, the central bulge, dark matter shroud, any major mass apt to nudge the route. Across millions of years, tiny errors in starting points and gravity fields snowball, yielding a spread of likely paths instead of one firm line. That spread widens with deeper time, swallowing various potential birth zones. Even so, the simulations steadfastly favor the thick disk over the thin one or outer halo groups. The craft's present speed direction, its tilt to the galactic plane, and its total energy all support a thick disk lineage. This won't isolate the exact host system. Ages of chaos have intervened, with countless tugs, but it funnels options to stars of particular eras, metal levels, and motion clans. Such a finding lifts 3I Atlas from curiosity to treasure. Thick disk wanderers seldom stray into our inner solar turf. Most space rocks probably spring from thin disk suns like ours, youthful setups brimming with metals akin to home. Thick disk relics grant glimpses of the galaxy's past, of elemental climates from billions of years pre-sun, and of world-building variety in a Milky Way far removed from today's form. Does this account for the odd makeup? Quite likely, in large measure. Ices around low-metal suns would gather varied frosts, dust blends, and carbon goods unlike those in solar comets. The carbon dioxide lead, the ruddy dust spectrum, even the quirky light scattering, all might stem from a birth chemistry molded by the parent star's atomic makeup. Studies on meteorites originating from metal-poor settings, though none exist in our collections, would likely reveal comparable anomalies compared to typical solar system compositions. Age presents another intriguing factor. Should 3I/Atlas date back 8 to 12 billion years, emerging soon after its host star, it would have roamed the Milky Way for durations that vastly exceed our solar system's mere 4.6 billion years. Over this vast time frame, the body has endured relentless cosmic ray impacts, ultraviolet exposure from nearby stars, collisions with interstellar dust particles, and fluctuations in surrounding radiation environments. Such influences modify surface compositions, yielding organic byproducts, remarkable crystalline formations, and the evaporation of volatile components from exterior regions. Consequently, an aged entity could exhibit behaviors distinct from its youthful counterparts. Surface volatiles might have been largely stripped away, forming protective shells that suppress sublimation until intensified solar warmth penetrates them. Interstellar grains could appear more weathered, with radiation-induced structural changes and coatings of organic polymers from photochemical processes. The peculiar polarization might stem in part from eons of environmental degradation that no comet in our solar system has undergone, given their relative youth. Talk of ancient spacecraft naturally emerges when exploring origins in the thick disk. Should advanced societies have developed there amid those primordial stellar clusters, possibly billions of years prior to Earth's formation, an 8-billion year, old culture could have colonized the galaxy, dispatched explorers to myriad star systems, or even vanished entirely, bequeathing only silent remnants to drift among the stars. If 3I/Atlas represents one such remnant, it would stand as a forsaken artifact, its mechanisms extinct, its purpose lost to time, its creators long gone. We would then be scrutinizing relics from a society predating our world. While this remains pure conjecture without backing data, it highlights how provenance narratives reshape interpretations. A thick disk provenance imbues an object with significance surpassing its material traits alone. It serves as a temporal voyager, a herald from antiquity, offering perhaps a unique glimpse into otherwise inaccessible cosmic conditions and dynamics. Even as a purely natural specimen, it holds immense scientific merit, justifying exhaustive analysis since its encoded insights are unattainable by any other route except direct voyages to thick disk stellar realms. Panspermia concepts from history lend yet another layer. If life emerged early in the galaxy's timeline, aided by metal-poor stars that still harbored habitable worlds, then ejected comets and asteroids from those primordial setups might have disseminated organic compounds, amino acids, or even hardy microbes to nascent systems. Panspermia operates without deliberate intent. Mere ejection mechanisms would do. Yet if 3I/Atlas hails from a life-bearing thick disk environment, it could harbor chemical or biological markers disclosing the presence, spread, and longevity of alien life forms. Spotting these remotely challenges present-day instruments. Sample retrieval for Earth-based lab scrutiny, employing methods precise enough to differentiate biotic from abiotic materials, uncontaminated from tainted samples, and ancient from fresh layers, would be essential. Still, the prospect excites, elevating 3I/Atlas from mere space junk to a possible cornerstone for astrobiology, a vital clue to life's prevalence across the galaxy, its interstellar migration, and whether we stand isolated or within a vast cosmic biosphere. Moreover, a thick disk source suggests interstellar travelers exhibit greater variety than our limited observations imply, with arrivals potentially from thin disk, thick disk, halo populations, or even interlopers from merging dwarf galaxies. Each would mirror unique birthplaces, elemental makeups, and developmental paths. Oumuamua, 2I/Borisov, and 3I/Atlas could embody separate archetypes, not mere variants of a single pattern. To map this assortment demands additional sightings, robust datasets, and deeper insights into galactic mechanics that funnel diverse objects toward our inner orbits. Prospectively, the thick disk theory yields verifiable forecasts. If accurate, 3I/Atlas's isotope profiles ought to diverge from solar norms, bearing traces of nucleosynthesis in metal-poor stars. Any detected organics might display atypical builds from alternate formation routes. Its dust mineralogy could feature compounds uncommon in solar materials, yet anticipated from low metallicity accretion. Upcoming spectroscopy enhancements, polarization mapping, and, with boldness and luck, a dedicated sample return endeavor could validate these ideas. Missions designed to capture interstellar travelers and return samples for in-depth lab analysis. Such prospects are still far off, yet entirely plausible. Advancements in tech are progressing steadily. Detection tools are getting sharper, and fascination with these cosmic drifters is on the rise. In the coming decades, we could be spotting scores of these intruders annually, scrutinizing them closely, and maybe dispatching quick-reaction probes to link up with the most intriguing ones. In this landscape, 3I/Atlas stands as a trailblazer. This entity compelled us to grapple with notions of stellar birthplaces, primordial reactions, and the idea that each interstellar arrival is one of a kind, bearing tales from uncharted galactic realms. Though we can't venture there ourselves, we can probe them via these rare wanderers that drift into our vicinity. Part 12. Positioning 3I/Atlas among interstellar arrivals. Spotting 3 verified interstellar bodies over 8 years of dedicated hunts sets a baseline for discovery frequency, though it hardly outlines the full roster. Every one has diverged sharply from the rest, hinting at vast variety in the void between stars, or simply that our dataset is too limited to uncover consistent trends. To grasp its contributions to our evolving view of the galaxy's nomadic remnants, let's juxtapose 3I/Atlas with its forerunners. Oumuamua showed up initially, picked up on October 19, 2017, via the Pan-STARRS scope in Hawaii. Its moniker, meaning scout or envoy in Hawaiian, fit perfectly. It marked the debut confirmed interstellar guest, even if later reviews turned up no prior sightings despite crossing monitored swaths of the heavens. Oumuamua's standout trait was its severe stretching, deduced from light fluctuations implying proportions near 10:1, like a cigar or maybe a flattened disk based on spin hypotheses. It lacked any obvious gas envelope or trail, even as it swung to within 0.25 Australian dollars of the Sun, deeper than Mercury's path, where ices ought to boil off aggressively. Still, Oumuamua displayed push away from the Sun beyond gravity's pull, pointing to some outgassing effect without a dusty display. This riddle ignited fierce discussion. Mainstream ideas pointed to hydrogen frost, nitrogen chunks, or faint vapor release yielding fumes but scant particles. Wilder theories, pushed by Loeb, proposed a manufactured source, like a solar sail driven by photon pressure. The argument lingers, with the majority of stargazers leaning toward organic causes while admitting Oumuamua was truly odd. 2I/Borisov turned up next in August 2019, found by hobbyist Gennady Borisov, and it acted predictably. It sported a distinct gas cloud and streamer, with spectral analysis revealing water steam, carbon monoxide, and standard comet gases. Its makeup stood out for elevated CO levels, implying birth in the chilly fringes of its home stellar setup, yet nothing wildly off-kilter. Light polarization readings were typical, particle ejection matched norms, and extra poles matched routine gas-driven comet dynamics. Borisov embodied the interstellar comet we'd anticipated, offering comfort that not every outsider is bizarre and that standard rules apply in distant suns as well. Enter 3I/Atlas, blending traits, more lively than Oumuamua, subtler than Borisov, settling into an awkward in-between. It boasts a gas halo, proving it's reactive, yet no evident streamer, implying muted particle output. Its makeup is atypical yet feasible, led by carbon dioxide in proportions odd for local comets, but reasonably tied to cosmic roots. Its light twist is intense, but stays within nature's limits if we consider quirky particle formations. Its motion hints at extra influences beyond gravity, though data on that is still debated. What insights arise from pitting these three against each other? Primarily, variety is undeniable. These interstellar sojourners resist fitting one mold. They differ in dimensions, forms, ingredients, vigor, and actions, much as our own system's icy and rocky bodies diverge wildly despite shared roots. This implies that world-building and expulsion mechanisms function comparably galaxy-wide, varied by factors like star size, element richness, disk heat gradients, and massive planet setups to yield broad results. Next, oddities may be the norm. Out of three, two sparked enough surprise to fuel expert clashes. Oumuamua's thrust sand streamer, 3I/Atlas's active glow without dust trail or quirky mix. Should this hold, the bulk of interstellar items will defy predictions somehow, whether from genuine contrast to our locals or because spotting quirks, brightness, or quirky paths make them stand out for detection and examination. Finally, our grasp stays tentative. Every fresh arrival demands theory tweaks, simulations refined, premises probed, fresh processes considered. This represents a positive step in scientific development. It shows that the discipline remains dynamic and adaptable to new evidence, rather than hardening into rigid beliefs. Yet, it also underscores our limited grasp of interstellar object groups. Do the majority resemble Borisov, with Oumuamua and 3I/Atlas as exceptions, or is Borisov the unusual one, and oddity the norm? 3 observations alone can't resolve that question. Advances in detection will soon swell the dataset dramatically. Once the Vera Rubin Observatory is up and running at full capacity, it could spot dozens to hundreds of such visitors annually, amassing datasets substantial enough to distinguish genuine trends from mere chance fluctuations. In just 10 years, we may determine if carbon dioxide prevalence is standard in comets from specific origins, if most display faint tails, or if non-gravitational effects usually match solar warming or point to alternative mechanisms. Doubts will shrink, giving way to insights grounded in solid data. Meanwhile, intriguing theories linger about constructed artifacts. Should a small portion of these wanderers prove artificial, say, abandoned scouts, remnants of light sails, or tech remnants, higher discovery volumes could uncover them via odd statistical patterns. Maybe specific dimensions appear oddly abundant. Maybe paths cluster unnaturally near the ecliptic or around planets. Maybe spectral readings flag substances too complex for natural origins. Such clues would be faint, demanding extensive samples to spot, but unmistakable once identified. On the flip side, all might turn out natural, with seeming quirks stemming from viewing biases, tech constraints, and incomplete theories. In 2 decades, we could chuckle at our 2025 naivety, how we confused gaps in knowledge for enigmas, or pondered extraterrestrials when we just hadn't decoded the dynamics of fluffy dust clumps in metal-poor ices. Embracing such modesty matters. Progress in science stems from admitting boundaries, not holding on to puzzles once answers surface. The contrast also spotlights our gaps. We possess images, yet lack high-res close-ups. We obtain spectra, but not lab-grade mass analysis of samples. We track motions, but miss hands-on readings of gas release or surface traits. Each cosmic drifter has been probed from afar, across millions of kilometers, via scopes pushed to their edges, decoded through proxies instead of up-close scrutiny. The real breakthrough in studying interstellar arrivals will arise from near encounters, probes dispatched to rendezvous, possibly even retrieval ops hauling bits home for detailed testing. Those ventures pose huge hurdles. These targets zip by swiftly and get spotted late, offering slim windows for pursuit paths. They're far off at detection, demanding multi-year chases even with prompt launches. Their scale and hazards vary wildly. Intercepting something like Rondu, an active comet spewing material, could wreck a craft via particle strikes or vapor blasts. Still, the rewards would reshape the field, converting fuzzy, distant scans into solid matter and energy facts that resolve ongoing disputes once and for all. For the moment, 3i Atlas enters the record as the 3rd verified entry. An eccentric yet perhaps unexceptional stand-in for the Milky Way's nomadic flock. It reminds us that the void between stars brims with fallout from world-building processes spanning the galaxy's timeline. That these drifters offer glimpses into chemistries and physics unreachable otherwise. And that each arrival is a bonus, unsolicited parcels at our door, demanding we observe and analyze them closely before they vanish into the void they emerged from. Time and more data will clarify if 3i Atlas ranks as the most captivating of the trio or merely the latest. Its slot in the lineup, however, is firm. A milestone in our slow broadening of perspective from the home system to the wider stellar network of roving remnants, linking suns via gradual swaps of rubble over vast distances and ages. Part 13. Recent astronomy news highlights. The cosmos defies our urge for narrow focus. As 3 Atlas draws focus, fresh celestial finds emerge in tandem, each with echoes that reshape our views of the universe, origins of life, and our role within it. Here's a quick look at the surrounding landscape from recent times, seeing how these concurrent tales enhance or clarify the motifs from our interstellar guest. In late September 2025, the James Webb Space Telescope released spectral data on K2-18b, a sub-Neptune world circling a red dwarf 120 light-years away. A vast distance separated us from the world. Spectral analysis revealed methane and carbon dioxide within its atmosphere, components typical for a hydrogen-dominated environment, along with faint traces of dimethyl sulfide, a compound that, on our planet, arises primarily from living organisms, especially ocean-dwelling phytoplankton. This finding is still provisional, pending further verification through more observations. Should it hold true, however, it could represent the inaugural biosignature identified beyond our solar system, shifting the quest for extraterrestrial life from mere speculation to tangible evidence. The similarities to 3i Atlas are understated yet significant. Each scenario demands careful analysis of unclear evidence, separating authentic indicators from background interference and instrumental biases, while balancing the demand for robust proof against exceptional assertions with the urgency of sharing preliminary insights before full validation. The dimethyl sulfide signal might stem from contamination or erroneous classification, much like the peculiarities of 3i Atlas could arise from observational inaccuracies or flawed interpretations. Nevertheless, both merit close examination, given the monumental consequences, such as the presence of life elsewhere or engineered artifacts in our cosmic neighborhood, that outweigh the slim chances involved. In the first days of October, a tremendous solar flare hurled a colossal plume of charged particles that just skirted past Earth, traversing the path our planet had taken only hours before. Rated at X5 intensity, this geomagnetic disturbance had the capacity to cripple orbiting spacecraft, overload power networks, and ignite polar lights viewable far from the poles. Our narrow escape owed more to chance than foresight, underscoring how space-based threats emerge without warning, and despite advancements in surveillance, our detection systems are far from flawless. Anticipating sunspot activity proves difficult, and charting the exact paths of these plasma bursts even tougher. This echoes the motif of unforeseen celestial events in 3I Atlas. We often view stargazing as a realm of precise calculations delivering reliable predictions. In truth, it's far more chaotic. Solar outbursts catch us off guard. Rogue wanderers from deep space materialize without notice. And our theories must evolve repeatedly as fresh findings upend assumptions. The cosmos owes us no predictability, and approaching its intricacies with restraint outshines over-reliance on partial frameworks. Further buzz surrounds revelations from the Euclid Space Telescope, deployed in 2023 to chart the sprawl of unseen matter and cosmic expansion over immense expanses. Initial datasets unveiled patterns of galaxies forming outsized cosmic webs, expansive gaps, and elongated threads, more vivid than computer models anticipated, hinting that either our theories of the universe's architecture need tweaking or these glimpses uncover subtleties overlooked by prior mappings. Scholars continue to debate fiercely, with experts racing to account for or refute the oddities based on their views of how solidly we grasp the cosmos's core makeup. Once more, the link to 3I Atlas runs deep on a conceptual level. The study of the stars routinely uncovers information that defies neat categorization. Sightings that test established paradigms, readings that prompt doubts over whether irregularities signal novel laws of nature or simply call for sharper control of errors. Progress in the discipline thrives amid this push-pull, fostering curiosity that sparks breakthroughs while applying caution to avoid misleading detours. Such stories also fulfill an educational role. They highlight how eccentricity defines astronomical pursuits. Surprise lurks around every corner on a weekly basis. Enigmatic black holes acting out of character, misplaced star clusters, detonations among stars that baffle simulations, alien worlds with outlandish traits. That 3I Atlas stands out doesn't render it exceptionally troublesome. It's simply par for the course in this field. The key differences lie in whether the oddity calls for enhanced measurements, upgraded hypotheses, or, on uncommon occasions, a complete overhaul of our worldview. Lay audiences often blur these distinctions, viewing each report as a harbinger of revolutionary change. Those who share scientific insights grapple with this mix-up, aiming to explain that the majority of quirks boil down to routine fixes, like improved tuning, polished simulations, or extra data patching holes, all while sustaining genuine thrill for those infrequent moments when true upheavals emerge. A verified biosignature on that distant orb would indeed upend our perspectives. The Euclid findings probably will just hone our cosmic blueprint without toppling it. 3I Atlas occupies a middle ground, possibly game-changing should its quirks defy everyday rationales, or merely intriguing if they yield to standard accounts. One lingering issue concerns the interplay among breakthroughs. If the dimethyl sulfide truly exists on K218b, does that boost or undermine the odds of 3I Atlas being of artificial origin? Proponents of the former say yes. If biological traces show up so readily on exoplanets in our vicinity, then advanced societies could proliferate similarly, rendering crafted visitors from afar more credible. Detractors counter the opposite. If biology is everyday, natural organic compounds are everywhere, so spotting them on 3I/Atlas doesn't indicate anything artificial. These two viewpoints rely on guesswork and lack solid evidence. We're uncertain about links between biological signs and tech progress, if smart civilizations often launch probes across stars, or if remnants are common enough to spot by sheer luck. Such logic is too shaky for firm judgments, functioning better as a thought experiment than rigorous analysis. Instead, these matching news stories provide backdrop. They highlight how astronomy in 2025 buzzes with energy, pushing ahead on several fronts at once. The James Webb Space Telescope is transforming our grasp of exoplanets and the universe's infancy. Sun-watching instruments uncover intricate magnetic flows in star behaviors. Vast cosmic mappings chart the cosmos's grand architecture with remarkable accuracy. Detectors for gravitational ripples snag merging black holes almost every week. Neutrino observatories delve into star hearts and exploding supernovae. In this mix, research on interstellar wanderers is blossoming into a fresh area, bridging orbital dynamics with planetary exploration, galactic history, and the search for life. This vibrant scene calls for steady patience and broad viewpoint. 3I/Atlas forms just one fragment in an immense puzzle, with countless parts still missing or unpositioned. Expecting instant solutions or clear verdicts is impractical. Knowledge grows step by step. Every sighting imposes limits. Each reading sharpens options. Every discussion hones ideas. This method irks those craving fast fixes, yet it proves sturdy and adaptive, unlike rushed agreements. Above all, these concurrent finds show the cosmos as perpetually captivating, no matter if oddities turn out ordinary or game-changing. Be it 3I/Atlas as a plain comet or engineered scout, or K2-18b harboring organisms or merely tricky reactions, or the Uckland structures needing fresh theories or improved models. The cosmos stays a wellspring of awe, enigma, and mental rigor, meriting our focus and labor, irrespective of how particular riddles settle. We pursue it not anticipating every find to rewrite laws, but driven by inquisitiveness, the joy of insight, and rare breakthroughs that redefine our worldview. For now, inquiry presses on. Facts pile up, and enigmas like 3I/Atlas sustain our involvement, impatience, and boundless intrigue for what's past our grasp. Part 14. Pulling it together. Insights from 3I/Atlas. We've explored sightings, oddities, ideas, and surroundings. Synthesis now demands effort, weaving scattered elements into a unified view, owning certainties, confessing gaps, and spotlighting key elements as 3I/Atlas's narrative evolves. Here, science bears its essence, not via absolute truths, but via candid review of proofs, doubts, and future paths. The ExoMars snapshot that started it all stays symbolic. It captured something far from standard forecasts. Lacking a clear tail amid an active haze, missing stretch from dust output, merely a tight blur that might mimic a far-off galaxy, save its drift amid fixed stars. This optical mismatch frames all that ensued. 3I/Atlas consistently challenges norms, yet stays feasible in nature's realm. Spectral readings expose carbon dioxide ruling at levels eightfold over water steam, flipping usual comet balances and hinting at atypical origins. Maybe from a dense disk, or lean metal early disk reactions, or selective gas escape over eons adrift in star realms. Each account feels organic and credible. Still, both edge 3I/Atlas to the fringes of comet groups, flagging it as standout, even for scarce star-crossing guests. Polarization data indicated a sharp low dip to -2.7%, far below standard comets, pointing to ultra-spongy dust clumps, rare particle mixes, or layers tweaking light bounce. Paired with reddish-tilted reflection patterns, evoking carbonate or organic-laden grains, these light traits sketch substances unlike intersolar samples. Once more, feasible yet atypical. The spin-based brightness shifts disclosed a 16-hour cycle with mild variation, implying a stretched but moderate core form, aligning with organic random rolls from torque. Conservation of angular momentum through its spin offers a sense of reliability. The object's tumbling mimics the behavior of ordinary celestial bodies, rotating according to unyielding physical principles without any signs of deliberate balancing or deliberate orientation adjustments that could imply engineered mechanisms. Disagreements persist over the kinematic data, with certain studies detecting thrust-like non-gravitational motion pointing ahead in line with Loeb's assertions, while alternative examinations detect sideways impulses aligning with typical comet outbursts, and yet more contend that the errors in measurements are substantial enough to prevent reliable identification. Such uncertainty highlights the challenges in accurate positional tracking for dim, swiftly traveling objects, and it will only clear up through prolonged monitoring that yields extended temporal spans. Models of its provenance, suggesting roots in the galactic thick disk, provide deep insight. Should Oumuamua have indeed originated 8 to 12 billion years back amid metal-poor stars in that disk, it bears elemental markers from eras when the cosmos was less mature, stars differed markedly, and worlds coalesced in settings far removed from the metal-abundant milieu of our own solar setup. This context renders every oddity more comprehensible, not as breaches of physical norms, but as manifestations of inherent variety stemming from formative conditions we have yet to explore directly. The atypical makeup poses no enigma demanding outlandish fixes. Rather, it serves as a portal to bygone galactic states, one we are fortunate to examine via this nomadic envoy from antiquity. Weaving these aspects into a unified account demands recognition of several plausible viewpoints. The cautious interpretation unfolds as follows. Oumuamua qualifies as an ordinary comet hailing from the thick disk, cast out from its home star system eons to billions of years past, bearing makeup traits that echo low metallicity birthplace chemistry, with particulate features modified by extended bombardment from cosmic rays and UV radiation en route through the void. It displays faint outgassing owing to sizable particles or sticky clumps, captured under suboptimal sight lines that truncate or conceal the actual tail with its subdued vigor, mirroring subdued vaporization from weathered, aged surface frosts versus pristine inter-system comets. This account demands no novel theories, drawing solely on mechanisms we've witnessed or postulated in other contexts, and regards Oumuamua as distinctive yet commonplace, a rare case within allowable ranges instead of a core threat to established knowledge. The majority of researchers endorse this view, deeming it straightforward and methodologically sound. The peculiarities endure in this framework, yet they fit as anticipated deviations across a varied group we're just starting to catalog thoroughly. The bold interpretation accepts identical data but prioritizes them otherwise. It highlights how numerous distinct irregularities, makeup, light scattering, absent tail, potential thrust, affect one entity, forming a cluster that taxes notions of pure chance despite each trait allowing mundane accounts. It underscores that interstellar agencies' hasty actions, such as redirecting juice, indicate official awareness that Oumuamua merits special focus surpassing standard probes of interstellar visitors. It carves room for unexamined options, conceivably novel particulate dynamics, perhaps unconventional reaction routes, or even, though highly conjectural, artificial beginnings. This outlook asserts no evidence for the extraordinary, yet cautions against hasty conclusions, affirming the enigma settled prior to full data collection, which could overlook true breakthroughs if Oumuamua defies prevailing models. It pushes for ongoing examination, fresh data gathering, and a mindset receptive to initially far-fetched ideas that gain traction with mounting proof. Straddling these extremes sits the practical stance. Certainty eludes us for now. The evidence remains unclear, the surveys unfinished, and restraint is called for pending key developments that impose fresh limits. Juice visuals could uncover outgassing structures as perspectives shift. Closest solar approach scans might reveal bursts of action illuminating particulate generation processes. Extended positional tracking could firmly outline non-gravitational influences. Further spectral analysis might uncover extra compounds revealing birthplace settings or evolutionary paths. Any such finding could alter views profoundly. A detectable tail in juice records would settle the primary optical puzzle, implying the initial sighting merely hit Oumuamua during an awkward orientation or low-output phase. Solar closest spectra displaying isotope balances matching primeval low-metallicity stellar realms would validate thick disk heritage and consider the unusual makeup of its structure. On the other hand, if the tail fails to appear even under peak sunlight exposure, that would intensify the enigma, prompting theorists to devise more innovative accounts for how a body that's clearly venting gases shows no detectable trail. The outlook for the coming period is clear-cut. Additional observations will resolve certain issues but spark fresh inquiries. That's the standard path in this field. Data collection addresses particular concerns, yet uncovers surprising intricacies that demand further investigation. The enigma of 3E Atlas isn't going to simplify overnight into something straightforward and completely grasped. Instead, our understanding will likely grow richer and more layered, with a few oddities clearing up on their own while others linger or evolve into novel challenges. Terrestrial telescopes will keep performing brightness measurements and spectral analyses as 3E Atlas travels along its path. The body should grow brighter nearing its closest solar approach, boosting detection quality and allowing assessments that are out of reach now due to its dim appearance. Experts in spectra will search for signs of rare isotopes, like the carbon-13 to carbon-12 proportions, levels of oxygen-18, or deuterium to hydrogen ratios, which disclose the backstory of its creation and the heat levels during formation. Such proportions offer profound insights, capturing details on the original star's metal content, variations in heat across disks, and the ways chemicals were altered, all pointing clearly to the settings where it originated. The essential way to grasp 3E Atlas lies in appreciating that we're seeing scientific discovery unfold live, complete with doubts, disagreements, and stepwise improvements. No cover-up exists, no concealed findings suggesting extraterrestrials, no exclusive insights kept from everyone else. The debates over data, rival explanations, and open admission of unclear points represent the true workings of research. It's chaotic since the cosmos is intricate, tentative because readings are tricky, and contested because experts with varied backgrounds reasonably draw different conclusions from vague evidence. This openness holds real worth, despite the irritation it can cause. It shows that science involves not just a pile of certainties, but a systematic way to pursue reality via methodical watching, thoughtful analysis, and group discussion. 3E Atlas serves as a prime example of this approach in action against a true puzzle, not the fabricated riddles of plots or fake science, but the authentic unknowns that emerge when the universe throws unfamiliar setups our way, requiring steady monitoring and deliberate reflection to unravel. The central intrigue endures. Suppose the odd features refuse to straighten out conventionally? Imagine if later checks verify no tail at all. If spectral data uncovers implausible elemental mixes, orbital behavior indicates boosts not accountable by gas release, and mounting proof compels us to entertain ideas now seen as overly speculative. When does the merely peculiar and ordinary tip into demanding entirely fresh theories? There's no fixed line in science. It depends on the shared assessment that builds via shared papers, expert critiques, meeting discussions, and slow agreement. Right now, that shared view favors everyday origins, yet it stays flexible to new findings. Should upcoming data firmly exclude standard comet actions, say, no trail possible under any alignment, propulsion clashing with evaporation rules, or substances implying tech beyond our reach, then opinions will adjust, slowly and reluctantly perhaps, but surely, thanks to the field's core trait of adapting when facts require it. Currently, 3E Atlas sits in that ambiguous zone linking the routine and the remarkable, the solvable and the baffling, the call for waiting and the urge to decide. It urges us to embrace doubt, avoid hasty judgments, and stay modest in the face of intricacy. These are tough habits in a society hungry for instant solutions and firm declarations. But they're vital for those seeking real insight into cosmic workings, not just our wished-for versions. In essence, the key is a mindset of receptivity, to proof, to updates, to the unforeseen. 3E Atlas might prove a standard comet from far-off sources with quirks that yield to explanation, or perhaps something odder that demands more info and broader models to comprehend. The straightforward truth is we're not there yet. We're investigating, and that ambiguity is precisely where discovery thrives most dynamically. Part 15. Broader consequences, potential dangers, and key areas to monitor. Each bit of cosmic watching extends its reach far beyond the initial focus, influencing linked fields of study and sometimes brushing against unanticipated topics. 3E Atlas, no matter the final word on its peculiarities, has already sparked ripples. It's important to evaluate this for advancements in cometary studies, populations of interstellar objects, the variety in planetary systems, and the remote chance of spotting technological relics via astronomical observations. Even if 3I Atlas turns out to be completely natural, its significance would still be profound. Such a finding would illustrate that comets wandering between stars display a wider array of compositions and behaviors than those confined to our solar system, mirroring the diverse settings where they originated throughout the galaxy's past. This variety would support the idea that every planetary system has its own distinct character, influenced by the host star's metal content, the chemical makeup of its protoplanetary disk, the migration patterns of gas giants, and numerous other factors that vary from one system to the next. The field of astronomy would develop a more comprehensive classification for cometary bodies, moving beyond perspectives centered on our solar system to broader galactic frameworks that include metal-deficient types, carbon-rich varieties, long-processed ancient specimens, and categories we haven't conceived of yet. This broader scope would advance the physics of comets by offering real-world test cases, bodies shaped by varying conditions, to probe our theories on how makeup influences activity levels, how dust traits rely on starting chemistries, and how sublimation processes shift based on volatile compositions. Every thoroughly studied interstellar interloper serves as a crucial data point, honing our models and evolving comet research from mere observation to foresight, from ad hoc analyses to solid statistical models. Should oddities linger and defy straightforward natural accounts, the consequences would intensify sharply. A continuing lack of a tail amid intense outgassing might prompt a rethink of how dust is generated, potentially uncovering fresh insights into particle clumping or electric influences overlooked by existing theories. Acceleration pointing ahead without matching sublimation thrust could indicate unidentified influences, maybe more potent solar-wind interactions than anticipated, or magnetic interactions with the ionized envelope in unforeseen manners, or radiation pressures on irregular shapes yielding surprising motions. These would qualify as natural processes still, yet they deepen our grasp of nature's breadth, injecting layers of intricacy into paradigms we assumed were settled. Scientific fields advance precisely via these broadenings. Anomalies get resolved through enhanced comprehension, not by discarding fundamental principles. Astronomy's past brims with such instances. Neptune deduced from irregularities in Uranus's path. Dark matter proposed for unusual galaxy spin profiles. Dark energy called upon to explain the universe's hastening expansion. When tackled with precision and innovation, puzzles spur breakthroughs. The most revolutionary outcomes would stem from confirming 3I Atlas as artificial, although that's exceedingly unlikely based on what's known so far. Uncovering tech-made objects would rank as humanity's greatest find ever, settling the question of cosmic solitude while sparking myriad inquiries into how common, what kind, and what becomes of advanced societies elsewhere. The effects would ripple across all spheres: scientific inquiry, philosophical thought, religious beliefs, governance, societal norms, as we confront proof of alien minds. Yet this scenario demands exceptional proof that's absent today. Precise shapes visible in detailed imagery, organized radio signals picked up by arrays, substances unable to arise without intent, or maneuvers breaching energy rules or hinting at deliberate drives. Nothing like that has surfaced. Lacking such, an artificial source stays in the realm of conjecture and amusement, not testable science. The main hazards in probing this involve reputation and how resources are distributed. Building up 3I Atlas as possibly engineered without backing evidence could lead to widespread disappointment once ordinary causes surface, eroding trust. Repeated false alarms condition the public to brush off real advances later, fostering that classic tale of the shepherd who lost credibility. Researchers need to weigh willingness for surprises against the duty to convey odds and data reliability forthrightly. Diverting resources unevenly presents another concern. If 3I Atlas seizes outsized focus and observatory slots beyond its true worth, vital alternatives languish. Astronomy contends with tight budgets, scarce observation slots, restricted funds, finite teams. Each moment aimed at 3I Atlas means less for probing exoplanets, tracing galaxy development, tracking stellar explosions, or myriad other pursuits. Prioritizing 3I Atlas requires grounding in its inherent value, not media buzz or wild guesses. On the flip side, skimping on effort holds dangers as well. If 3i/Atlas stands out as a true outlier that demands thorough investigation to grasp its nature, limited sightings could let it slip away before we gather essential data, creating lasting voids in our comprehension. This interstellar interloper visits just once and vanishes forever. Failing to examine it in depth would mark a shortfall in research focus, yielding to budget limits even when the rewards warrant bold investment. The key milestones ahead are straightforward. Perihelion transit promises peak dynamism and optimal viewing setups. JUICE spacecraft snapshots deliver fresh angles and tool functionalities. Extended positional tracking pins down its motion precisely. Spectral surveys seek out elemental markers and chemical compounds. Polarization analysis hones in on particle traits. Every stage could clarify oddities, verify them, or pivot them into fresh puzzles needing further probes. What signs should observers track? A visible tail would indicate standard conduct, recasting 3i/Atlas as a fascinating yet ordinary case. Ongoing lack of a tail amid intense solar warmth would amplify the enigma, prompting innovative theories. Elemental proportions affirming origins in ancient metal pore zones would bolster the dense disk theory and account for quirky makeup. Unusual elements, say deuterium levels clashing with familiar star systems, would spark deep inquiries into its source and essence. Spotting intricate carbon-based molecules via spectra could suggest primordial life-building processes, intriguing exobiology without confirming life. Discovering basic shapes in enhanced photos would spark rigorous analysis. While natural forces can yield oddly precise forms, like hexagonal pits, straight cracks, or even jets, symmetry by itself wouldn't confirm artificial design. Signals and radio waves at odd wavelengths, or with modulation defying ion behavior, would prove astonishing, urging swift verification and cross-checks. Realistically, answers will unfold incrementally and leave some wanting. No one finding will resolve everything, but building data will gradually steer views toward earthly rationales that embrace 3i/Atlas's quirks sans wild ideas. A subtle tail in future views might arise from delayed activation by outer layers. Its makeup could align with norms for dense disk bodies after surveying more examples. Polarization data might match revised simulations factoring in old cosmic rays. The tail would conclude quietly, as a noteworthy entry in comet records, not a game-changing discovery. Yet a slim chance lingers, faint but real, that 3i/Atlas truly defies our paradigms. That slim shot alone merits the focus, the probing, the funding poured into decoding it. For if it defies natural origins, if quirks resist explanation, if clues build toward radical options, the fallout reaches far beyond stargazing. We'd face hints of minds elsewhere, tech voyaging across voids, our place in a vast stellar network revealed via this lone, odd traveler. This closing reflection loops back. ESA's initial shot wasn't meant to appear so peculiar. No tail, tight form, puzzling aura. Still, there it sat. Pixels forming layouts that bucked predictions, yet stayed plausible. And perhaps that's the essence. Perhaps the cosmos, via 3i/Atlas and myriad other puzzles, reminds us our theories are tentative, our grasp partial, our classifications too stiff for the universe's rich variety. Perhaps the right approach avoids cramming data into old slots or rushing to bizarre conclusions, but instead embraces the unknown, probes steadily, and stays receptive to truths from diligent work. 3i/Atlas presses on, hurtling through the sun's core realms at 86 kilometers per second, indifferent to our gaze, arguments, dreams, and guesses. It will hit perihelion, maybe bursting to life or staying eerily barren, then drift outward to the system's fringes and ultimately to the stars, merging into the grand, leisurely flow of cosmic stuff. We'll observe till it dims past sight, squeezing out every light scrap, every chemical trace, every orbital limit, then await the next wanderer, the fourth verified starfarer, pondering if it'll act predictably or pile on more riddles to our expanding archive. That anticipation defines our era, amid wanderers, amid watches, dwellings in the space linking conjecture to validation. It's disquieting yet truthful, ambiguous yet thrilling, irritating yet mentally vibrant. This represents the true nature of scientific inquiry, the genuine expansion of understanding. The real way humans grapple with a cosmos that defies easy accommodation to our whims. The three Atlas imparts endurance, modesty, and awe, not via conclusive resolutions, but via enduring inquiries, startling insights, and the enduring chance that, on occasion, truth proves more bizarre and enchanting than our boldest visions.